Exchange 2023. It's so wonderful to have you all here. Welcome to our online audience as well. It gives me great pleasure to introduce our director, Professor Edmund Linfield.
Any applause, I have to say, is for Andy and for everyone who's actually put this together, and it's certainly not me. So I can only really add to Andy's welcome. It's really great to have everyone here today to explore a whole range of materials research we've got today, a fantastic set of posters which we'll go and see over lunchtime, and hopefully many, many interesting discussions. I will say in advance, thank you very much for our external advisory board who are scattered around the room here, and it's really good to have you with us and for all the advice you give the centre. And also for those that have come to visit today to give the invited talks from outside the University of Leeds. I would say as well that we really welcome those who are going to be watching the live stream, and we really hope you as well enjoy the day, and next year do come and join us in person rather than just be the live stream. So, without further ado, what I'd like to do is welcome our Deputy Vice-Chancellor for Research and Innovation, Professor Nick Plant, who's going to come and say a few words just to start things off. So, Nick, over to you.
Good morning, everybody, and welcome to the Bragg Exchange 2023. It's lovely. Last year, I gave a welcome virtually. It's fantastic to be in the room this year and being able to talk to you. So the university, as many universities do, has a grand vision statement about how we can create expertise in research and education to transform lives and shape a better future for the world. The question is, what does that actually mean? And I think the answer is Bragg, and I genuinely mean that. Bragg is the epitome of what our university strategy is about. Let me walk you through why I think that's the case. So last year we saw the official opening of the Bragg building, and the Bragg building is a fantastic state-of-the-art building that is both teaching and research, and acts as a focal point to bring people together. And the Bragg Centre for Materials Research sits at the core of Bragg, because we've seen in the last year the membership grow further. Importantly, we've seen the mix of people who work there grow, and that's across career stages. That's in terms of diversity of the group I see sitting here, and in terms of the disciplines that come to work in the area of materials and apply it to both fundamental and challenge-led research. Bragg has also really helped us to grow our partnership working with industry, to be able to take the great research we do, the great people that we train, and put them out into the world where they can become a success and fulfill their career aspirations. Not only that, we can help them take the knowledge to create some real, tangible products that will make the world a better place. And ultimately, when you become rich and famous, don't forget where you came from and come back and become part of that pattern again. Preferably a large donation would be nice. But also, I think something that Bragg has done brilliantly is the way it really encompasses both the cutting-edge research and the educational side, whether that's undergraduate, postgraduate, or outreach activities. Bragg is inclusive. Bragg is about the fact that materials matter to everybody. This is why, for me, Bragg is special. So yesterday we had, as part of our EPSRC Strategic Partner Programme, we had a meeting with the Executive Chair, Lynn Gladden, and Edmund was one of the presenters talking about the Bragg Centre. And what I loved about Edmund's presentation and what Lynn loved about it was that we talked about excellent research, but actually that was almost a given. What really excited her was the outreach work, the DNA origami that Andy led. It was the fact that the Bragg building has transformed the way we operate by bringing the pieces of equipment, many funded through the collaboration with Royce, together. That allows us to bring the technicians, the experimental officers, the researchers together, so you can share experiences and grow and collaborate much, much faster. That, to me, is why Bragg is the epitome of what the university strategy should do, because it places people and collaboration at the heart of everything it does. And then excellent research and excellent people just naturally come out of it. I hope you have a fantastic day here today. There's some great talks coming through. Way over my head, I'm a biologist, but I think the key thing is you're here, whether it is physically, whether you're watching the live stream or you will watch it later, you are part of the Bragg community. And what you will do is you will pay it forward. You will become part of the success and part of the enjoyment of Bragg. So thank you all for coming here today and have a fantastic day. Thank you.
Now, I think we might need just a little bit of logistics before we start. And there's a few people who've crept in the sides, very welcome. But you might find you want to just move a bit to the other side just to get a better view. So if you want, just anyone wants to move towards that end so you're looking at the screen rather than looking at the side, do so now. So if anyone wants to just take a step across so they can see better, there are plenty of seats at the back. So well, let's just do that now.
Yeah. So while people are moving around, there's just a little bit of housekeeping. Andy, you want? Yes, just a little housekeeping. So hopefully everyone's seen our code of conduct for events before. It's part of our EDI mission to make sure that everyone feels inclusive. It's printed in all of our delegate guides as well. There's no fire alarm today. The fire alarm test was this morning, bright and early before anyone arrived. So if you hear a fire alarm, then we do need to leave. And we have to head out the building to the grass area out the front. There are plenty of people on hand for first aid today. If you need anything, then please just let a member of the team know, or a member of the events team as well. Toilets, there are toilets located just outside here and into the stairwell area, I believe. And there's certainly toilets downstairs by where all the coffee is going to be held. And just to make you aware, as mentioned multiple times, this is a live broadcast, so if anybody has a problem with that or appearing in the live broadcast, please do let us know and we'll make sure to kind of shuffle you out of the direct camera view. Just a final point then to say that most of the sessions, all the talks are in here today, and then at lunchtime we're going to head over to the refectory to do posters. We've got a stack of 70 posters to go through alongside an exhibition from our facilities as well, so you can understand a little bit about what research capabilities are going on in the centre. And otherwise, then it gives me great pleasure. Oh, coffee, yeah, sorry, coffee. There's coffee at both comfort breaks as well. So one after the first two sessions in the morning. Hopefully you'll see that from the agenda cards that are scattered around. Coffee is taken downstairs where we arrived this morning, and there'll be one again this afternoon as well. Without further ado, I think we're fashionably late as always, so I'll let Edmund carry on the next session.
Right, well, welcome, and it's a real pleasure to welcome our first speaker, Professor Michael Shea, coming over to the University of Manchester with a tantalising title, which is Sustainable Plastics versus Sustainable Systems, One Bin to Rule Them All. Michael, over to you.
Technology is great. Let's see if this works. Okay, good. So thanks for putting me at the beginning when I'm talking about the end. A bit of a combative first slide. So I work in environmental sustainability, originally a chemist. Now I don't know what I am, but hopefully you guys can tell me what I am by the end of today. So why do I have this as the first slide? Well, we live in a time of great challenge. And we don't just have a single challenge, because we have global conflict, we have increasing dissent and siloed opinions, all while we are dealing with something which really could kill us all in climate change. And so what I want to talk about today is systemic views of why we have to think more broadly about sustainability, but also how materials are really important to thinking about those challenges in an interdisciplinary way, but also thinking about those solutions. So, actual title slide. So, sustainability, right? What does that mean? We're going to talk about sustainability in the context of plastics, and we're going to look at systemic views. So, I must say I'm a little bit uncomfortable because you're all smarter than me, and I deal with social science and economics as well as material science. But hopefully I take you through a couple of these stories. And the reason we think about social science is because it's all your fault, right? The way that we interact with the world, that's actually what goes and creates all of those consequences. So if we wanted to save the world, right, well, what should we drink our coffee out of? Should we drink it out of a styrofoam cup, or should we drink it out of a ceramic mug? So how many people would go styrofoam cup? Okay, cool. How many people would want to save the world by drinking out of a ceramic mug? Cool. So you'll note a lot of the older generation, maybe even some of the Bragg board, they didn't raise their hands at either time, right? Which implies that they are robots and they do not drink any beverages. When did I raise my hand, though? Well, I raised my hand for the styrofoam cup, because when we think about the energy and the embedded energy of materials and how we use them, and we think about our desire to solve this energy crisis, we have to understand that I can make, use, transport, and dispose of 500 of those styrofoam cups for the energetic cost of one ceramic mug, because I need to go and dig up clay and fire a kiln up to high temperatures and transport it to, you guys look like a Waitrose crowd. Waitrose, you've got to purchase it from Waitrose, bring that back home, right? And all of those steps are expensive. Expensive in terms of a monetary sense, but also in terms of energy. Now, the challenge here is not the styrofoam cup. It's actually really efficient. It's made by an atom economic process. It's extremely efficient. It's using a waste product from the oil industry. But the problem is that we think of that material as being valueless, and so that we throw it away. It's disposable, but we're not disposing of the ceramic mug. And of course, some of you would be going, well, I'm going to reuse the ceramic mug, so then I'm going to win. The challenge is when you think about the energy, you've got to wash your mug, make some detergent, heat the water up, remove the detergent from the water afterwards, and that's the energetic cost of 2 styrofoam cups. So energy is essential to thinking about those materials, but what we're doing wrong is we don't value plastics, and therefore we're not using them and recapturing their value. We think of them as not advanced materials, but stupid waste materials. And of course, when we think about the rest of our plastics universe, we understand that there is these significant energy and waste gains because we're using those plastics. So if I think of plastic packaging, I would quadruple the weight of plastic packaging when I switch to alternative materials. I would double food spoilage because I lose the exceptional oxygen barrier properties of those materials. My vehicles would be heavier, and so our petrol costs would increase. And we lose modern insulation that keep us all warm, right? Well, not necessarily British building standards, but the rest of the world. And when we think about that complexity, what we have to understand is that society's view of what that word plastic means is really different than what a group of material scientists would think. Because if I go and I look at the simplest area of demonization in terms of our plastic universe, I think of a grocery store. And of course, if I look at those packages of meat, I would say, oh, that's a plastic package. But it's not a plastic package. It means a lot more, because the switch to plastic packaging actually significantly increased our shelf life of food, meant that we had much less food waste. It improved food safety standards. Those are things we have to keep doing. So any material transition that we're imagining, we have to first maintain the properties that we're looking at. But of course, many things we do with plastic are not useful. So the meat in the top left, and by the way, for the vegetarians in the audience, you can also do this with aubergines. It looks sexier. and people pay more money for it. But it has a dramatic impact on the recyclability or the fate of those materials. It can't be sorted and actually leads to a less valuable product in the end. And so the things within those plastic universes, well, we need to identify what we have to keep doing and what we need to give away. So almost all of our research is done in collaboration with industry, and we do a lot of consultations to try and get them to do things better. But the complexity is really what makes this complicated and what makes it into a material science challenge. Because this is not a plastic package. It's a plastic tray, or perhaps a plastic reinforced paper tray that they're claiming is made of paper. The laminated film is 5 micron thin layers of plastic, each performing a different function, many of them having order to them. We have plastic adhesives and heat seals, a plastic reinforced paper label, and underneath we have that maybe adsorbent mesh, right, that soaks up the meat juice and prevents it leaking all over the rest of your groceries. So what do we want someone to do? So we were working with a packaging provider, and they were like, well, people just have to put this in the recycling bin, right? And it's fine. We could get people to rinse out a tray and put it into the recycling bin, and no one is rinsing out an adsorbent plastic mesh that's soaked in meat juice and putting it in the recycling tray. No one. And when we think about design, what we have to do is therefore put social practice first. We first think about the problem, how people are dealing with it, how the world is interacting with these materials, and then design based around social practice, not our own wishful thinking. So switching that technocentric approach to something which involves human behavior. This is Extinction Rebellion, when they stuck themselves to the London Stock Exchange. I didn't talk to these guys, but I did talk to Extinction Rebellion about plastics. Because originally they were very much, oh, we have to do it with all plastics. We should be a zero plastic society, without really thinking of the consequence of that. Because of course, when we think about the broader world of polymer science, textiles, PPE, footwear, electronics, and even the adhesive that is attaching this gentleman's hand to the London Stock Exchange are all the same material. This is all polymer science. And so that's that complexity of what we actually need to do. I threatened, when this converted over from Mac to PC, I said, you're gonna screw up my fonts. And I was right. So what actually makes this sustainable plastic, right? So how do we actually go and solve this? A sustainable plastic does not exist. There is no such thing as a sustainable material at all. So what do we do? Well, we have to understand value first, right? So we have to recognize that polymers hold massive societal value, regardless of where they are. That when we switch to an alternative, oftentimes those alternatives are producing more waste and more CO2. We secondly have to recognize diversity, right? So that diversity of both social practice in terms of their use and how they are composed requires a lot of different nuance and optimization. And so a lot of the policies that come out, oh, we're going to ban X, well, actually those don't work because they don't recognize that complexity. A really good example of this, the ban on plastic bags for a very brief period of time was going to ban blood bags, which were used to give people blood, because it's a bag made of plastic. So what do? Well, we have to have multiple fates. So some things we need to reuse, some things we need to recycle, some things we might need to degrade, some things we need to pyrolyze. But we definitely shouldn't burn it, and we definitely shouldn't just leave it in landfill unless we really make those at a different material. And that's unlocking change because we're doing standardization and developing that. And so we are not looking for some sort of a plastic-free world. What we're doing is recognizing the value of these materials, recovering the economic and material value from those things by creating a sustainable system. So a sustainable plastic only exists if we have a sustainable system in which it exists. So if you're going to remember one thing from this opening gambit, it's this. It does not matter if something is recyclable or biodegradable or reusable if it is not recycled, biodegraded, or reused. We have to start being honest and using past tense terminology to actually examine what it is we're trying to do. So that is the pitch for what our research group is. We're increasing in size, it seems all the time. But I'm going to tell you about 3 little vignettes, 3 very short stories that kind of capture some of the things that we do in a practical sense. The first one is the one down at the bottom, right? So thinking about things that are cross-linked and thinking about MasterCard, how in the world are those related? Well, so when we think about those polymers, we have to understand that the general public thinks all of those are the same, right? It's a plastic. But of course, we, as material scientists, would recognize that we have both thermoplastics and thermosets. And of course, the thermoplastics and thermosets have really different functions. They have different opportunities that are captured within them. So thermoplastics, really variable properties, but poor solvent resistance, low thermal stability, significant stress softening. So I can use those for some applications, but I don't want to build a boat out of it, right? But a thermoset, well, now I've cross-linked those materials together, and so I get a very different set of properties. And they're still variable, but I've now increased the strength of those materials in many different ways. But the challenge comes at end of life, because if I want to think of those thermoplastics, well, those are those classic plastics which are mechanically recyclable or reusable in different forms, so upcycling or downcycling. We can have biodegradable thermoplastics. We could incinerate them, but we don't want to do that. And of course, thermosets don't really have a really good circular fate, right? So I could downcycle it by grinding it up and putting it into something else, but almost all of it ends up in landfill or incineration. So I'm going to tell you a thermoplastic story and a thermoset story about how we work with industry to solve a challenge they have to try and make this a better place. And so the story starts with MasterCard. So why is MasterCard so concerned about plastic? It's really shocking to see 6 billion cards per annum, right? I just checked out of a hotel this morning, of course, had my swipe card, handed that back in. Oh my God, it's a pandemic. That is never going to be reused, right? It's gross. I mean, I was licking it the whole time. So it has to go into some disposal system. 6 billion cards. That's 30 million cards. Almost all of those cards are currently made out of PVC, right? But it's not just PVC. Of course, we have this wealth of different materials. It's a laminated structure. We have a barium magnetic strip. We have a whole bunch of different metals in there with the antenna. That complexity makes recycling really difficult. And so what we did with them is reach out to them once they made a big announcement, because they said, oh, we have the world's first biodegradable credit card, which of course biodegraded and released all of those metals and the inks and dyes and the barium into the environment. Great idea. And so that idea of working through unintended consequences of product design is really important. So if I think of a circular card economy, actually, there is a lot of value in that material. So about 80% of the price of the card is captured in the rest of that. And so if I want to go and have a circular system, I have to think about a chemical recycling strategy where I can separate those out. I could separate it out into different layers, but that takes a lot of solvent and is really difficult. Or I can go chemical recycling. And so this is the first example of what we did. Just chop the card up, put it into ethylene glycol with a catalyst that we're not telling you about, and get that to work really, really simply. It takes about 20 minutes. We can scale this up. So in our labs, we have a 20-liter reactor. I think this is actually our 10-liter one. So we've done 300 cards, recycled completely in 20 minutes. It doesn't take exceptional skill. You just need to be able to stir, right? We're lazy, so we got a mechanical stirrer to do it. But if you really want to do it, you can just stir it yourself. At the end, what we get is something which is really easy to separate with water. So a single water-based purification step allows us to recover the plastic material on the left, as well as the rest. And so I can take each one of those different components and circularize each of them. But I can take that resin and directly repolymerize it to be able to make a new resin for a credit card. So circularity is really important here, but the whole economics and life cycle of it is driven by the rest of those materials. So instead of thinking about plastics only as those, oh, okay, it's a bag, what can we do with the rest of our plastic universe, and how do our decisions about fate change? We can take that same idea of including functionality and backbones in thermosets as well. In this, we had a second requirement because there really were not effective cross-linking materials that were out there, so we had to design our own. So this is the molecule that's shown up here called Bistox. It's actually based from tartaric acid, but it's really important because the rigidity of that chemical functionality, where we're locking in those two cross-linking pieces, is actually really important to tuning the function. And what we can do is take the rest of that material being bio-based and then create an entirely bio-based and entirely biodegradable thermoset. The important thing out of this is that it's an atrocious idea to do biodegradation out of that as a framework. But of course, just because something is biodegradable doesn't mean that that's the preferred fate. So what we can do with these materials is actually do the exact same chemical depolymerization and actually recover the materials from this. The materials are self-healing, so I can reprocess them either by putting a little bit of stress on that or adding a little bit of solvent. And they're vitrameric, so I can actually reprocess these thermosets into new form. But importantly for us, this was the idea of having fiber recovery from systems. So I'm showing our work on glass fiber because it's easier to see. We've also done this on carbon fiber, where we can make a composite material and then do that depolymerization and recover either the carbon or the glass fibers back without affecting their properties or structure at all. So we're not having to change their signs. And of course, this is important from applications like fiberglass all the way through to circular wind turbine blades. And I'm not allowed to tell you who we're working with here, but it is someone. So that's the first story, circularity, but you're choosing the fate based on what makes sense for the material and in consideration of all of the other materials that you have. The second one, told me this one was going to work too, is one bin to rule them all.
When you hear the term plastic recycling, do you know which plastics are actually recyclable and which aren't? Come to think of it, do you know which plastics can be recycled, full stop? In the UK, there are 39 different household bin collection regimes across 391 local authorities. For example, you can recycle a plastic bottle in one local authority, but not a plastic tub. Yet in another authority, you can recycle that plastic tub. And it's not just domestic recycling that's confusing, but disposing of it when we're out and about too. But what if there was one bin that could simplify the whole plastic waste system? A single bin for all plastics. For the consumer, it would be incredibly simple. One bin to rule them all. This project aims to simplify the whole system, eliminate the plastic released into the environment, and prevent it ending up in landfill or the incinerator. Instead, the value of plastic will be recovered by determining the best pathway for it once it enters the waste infrastructure. The public disposes of their plastics into one bin, where it is then sorted. This can be done using a new marking system added to the plastic at the point of manufacture, either by printing a small code on the plastic, which cannot be seen with the naked eye, or by embedding it into the molecular structure. Both of these methods can be detected using spectroscopic techniques. The markings are used to sort plastics into bins for reuse, mechanical or chemical recycling, choosing the best fate rather than simply mixing the same plastics together. By working to develop solutions with everyone in the plastic supply chain, from manufacturers and brand owners to local waste management, all points of the chain can share the value of these recovered plastics. The one bin for all plastics brings together a focus on materials, business models, and social practices to create a holistic solution to tackling plastic waste.
When you have leftover money in an EPSRC grant, you can actually pay someone to do animation for you. And what starts as a joke, as a title, now is something that they will probably print on my gravestone. So, good. So when we think about a credit card and a thermoset, we actually have a simplicity of waste management, because none of you is going to go and give me your credit card, right? we're going to capture the value of that in a different way at end of life. And composite, we have different mechanisms to capture those materials. They're not being disposed of in the home. And in fact, in the home, we have the most complex social environment in terms of how people are using that material. And the inconsistency of practice actually was leading to a lot of contamination within those waste management chains, and that was leading to lower quality products. And the challenge is that we're currently sorting based on polymer type. So of your pots, tubs, and trays, about 1% of those are laminated with polyethylene, right? And of course, when I recycle polyethylene with polyethylene terephthalate, I now get a worse quality polyethylene product and a worse quality polyethylene terephthalate product because of that lamination. So there is a material consequence to the fact that we're sorting materials in a different way. What this looks at is really what are the material consequences, the economic consequences and the social consequences of doing things in a more holistic and open way. So it's very interdisciplinary. We have social scientists and economists in our team. We've done full life cycle and environmental impact assessments on the work that we're doing. And we have 27 industry partners just on a single project looking at this. So this is a really neat approach in terms of actually doing trials. As in, we've put bins in people's households in Greater Manchester. We've interviewed them about their practices. And those really explore the types of opportunities that we have. And what's fantastic is it's really engaging, because when I say to my team, oh, what do you want to do this weekend? They say, let's go to the dump together and sort through waste that people put in their garbage bins. So I have a remarkable team in terms of their willingness to get stuck in on this and donate their time on a weekend. But what's the actual outcome? Well, the outcome of this is a quite complicated material hierarchy, because there are decisions we need to make, but there is actually an optimal order to the decisions we need to make them. And decisions might be made because they improve our waste management, right? So they eliminate a contaminant, or they segregate different types of grades, so perhaps segregating based on melt flow index. And all of those are potential decisions. But the hierarchy has power because it can inform both the present and the future, in that it allows us to make decisions on what we should do with the infrastructure we have right now, as well as inform bays as to what investment they should be making in tomorrow's waste management structure. It's interesting here, we actually just need more mechanical recycling. That's the first thing that we need to do. And then we can start doing posh things like chemical recycling in a broad scope. That doesn't mean chemical recycling is not important for already pre-segregated waste streams, but the challenge is that we need to actually build up our infrastructure in a base sense. Sometimes those questions, though, are unknown. So for the first time in the United Kingdom, we are going to have access to food-grade polypropylene. So that means your yogurt tubs are going to have recycled content in them for the first time. And nobody had actually looked at whether this was a good idea or whether it was safe. So we've worked with a lot of the suppliers to look at both blown films and cast film products to be able to look and see whether or not this is actually safe. So we do a lot of practical experiments to answer those questions to build the hierarchy. But the reality is the hierarchy is simple because it's meant to inform government, and you have to keep things simple. Being recorded on YouTube as I said that. Crap. Anyway, keep things simple, politicians. But of course, this raises two questions. Number one, how do we know whether or not a content is recycled in the first place? And number two, as we're going and making these claims of recycled content, are we ruining the trust that we're trying to build up with that? So that led us to the final project that I'm going to talk about, which is actually about how do you quantify recycled content in a plastic package. So you look at this water bottle, what's the brand? This water bottle will probably be 70% recycled content, right? So if that's 70% recycled content, how do I know? It looks like a bottle. They've put a little bit of blue dye in it to make it look cleaner, which is what they have to do with recycled content. But is it 70%? And the challenge here is that the UK brought in legislation called the plastic packaging tax that mandated 30% recycled content in all plastic packages, with literally no ability to actually determine analytically whether we had that. So we invented one. A lot of times people say, oh, I will tell you what I bought, right? So I bought this amount of recyclate, and I bought this amount of virgin plastic, and I can do long division. But just because you bought something doesn't mean you could use it that way. We had one company who was incinerating waste plastic for energy in their plant and then claiming they were using it in their body. So what our technique is, it's actually really simple. It's basically just using tracer systems, but the tracer has to be quite unique. This is a fluorescent marker that has a bathochromic shift when it aggregates, and I'll show that on the next slide. But basically, this is a fluorescent material where I can determine concentration without having to reprocess the material. And so that bathochromic shift allows us to quantify on the end product without any extra reprocessing. And so the way I do this is because we have this shift, it allows us to normalize spectra and basically take the ratio between two different peaks, which is our dimer and our monomer, and actually then look at linearity across from about 5% up to 100% recycled content in those systems. Many people have said to us before, especially when we talk to industry, oh, well, someone's just going to go and add something in there and then fake it themselves. Well, we have a lot of information, actually, when we look at the history of how that has been processed, which are unlocked by looking at fluorescent lifetime measurements instead. So we actually have 2 methodologies that we've disclosed and a third that we don't tell anybody about to prevent fraud, to be able to sort of assess how these dimers and monomers are existing within the plastic environment. Importantly, the way that that is interacting with the base polymer is really important to those structures. And so if I look across different packaging types, I always see a linearity, but that linearity or the slope of that curve depends on the base nature. So the bottom 2 lines here are polyethylene terephthalate and polystyrene. Both of them have aromatic groups, which interfere somewhat with the aggregation phenomena that we're seeing. And so the more aromaticity you have within your polymer, the smaller the slope and the higher you would need a loading to be. But each one of those calibration curves sort of represents what you would do for that packaging market, and it's about 60% of the total plastic demand in the EU just captured by this. We have done a lot of work trying to stress test this system. And in fact, just last week, we've done our first 1-ton trial with a recycling partner here in the United Kingdom. It's entirely process independent, it's sample size independent, it doesn't get affected by different additives that we're adding in. It works for colored plastic, so if we go back to the beginning on that black plastic tray, we can actually now sort the tray if we wish. It doesn't impact the material properties. Everybody else wants to impact material properties. We don't. Keep it the same. Compatible with lots of packaging practice. And once we bring that back through, we can actually recalibrate and then re-loop the material as many times as we want. So just to close, we've actually started up a not-for-profit. So rather than going and creating a corporation, we set up a not-for-profit to be able to commercialize this. We're working with a number of partners to launch a trust mark certificate, as well as inform on the plastic packaging tax, which HMRC seem to be on board with. And this is really all to try and address circularity and trust within these markets. So 3 stories, right? One about systemic waste management, one about building trust by using analytical methodologies, one by choosing the fate of multi-materials in those systems. Those 3 stories are a really small part of what we do. So Chris and Toric, they work on the One Bin project. Zoe and Tom work on Recon, and Peng works with MasterCard, and Fiona and Eloise work on the crosslink systems. But everybody else is doing all kinds of interesting stuff as well. So hopefully I get a chance to talk to you about some of those other things at some future date, but just remains for me to thank all of the funders who are really supportive of our work, the team who are just a remarkable community of people, and you for your attention.
Thank you. What a fantastic start to our day. That was a really interesting talk. So we have questions, I think, and I think there's a microphone we'll take around. Are there questions? Yes. Jeremy. And if people want to move to other seats, please do that as we go between sessions.
Oh, thank you for a great talk. You mentioned the mechanical recycling is one of the things to concentrate on, and I wonder if you want to talk a little bit about low-energy forms for mechanical recycling and how big a barrier that is and the challenges there.
Yeah, so I think it's really quite interesting. There are a lot of additives which are used to increase the properties of your recyclate are actually introducing cross-linking and requiring more energy input in terms of that mechanical recycling process. And I think that that's a really careful balance. Our view is that you really have to segregate grades and keep the things together so that you're mechanically recycling a homogeneous set of materials. That allows you to tune things. There are other additives. If you're doing a single mechanical recycling process, right, where you can kind of capture microwave energy or ultrasonic energy in order to lower the energy barrier for mechanical recycling, the challenge is that it's really difficult to take those through another route. So something like plastic packaging, probably not the best way to do that, but a polypropylene downcycle into a park bench, I think is a really good methodology there. The key is all about controlling processing conditions, and the consistency of that across markets is sometimes difficult.
Can I ask a question, which is, obviously you're working with a lot of companies. In this space where all the companies have similar problems, how easy is it for those companies all to work together collectively on a solution as opposed to wanting the solution to be their own solution? And I'm not quite sure how the competitive versus collaboration works in this space.
Yeah, the major packaging producers are giant babies, and they don't like working with each other. And that is a real limitation in terms of consistency. So when we think about consistency, our view is that that has to be legislated, right? So this is where we work a lot with national policy, with OECD, to try and drive consistency from a policy perspective as a way to motivate that. They all have the same aspirations, and so that's why if you take the One Bin project, everything is open data. And so open data sometimes unlocks change as well.
Hi. Thank you for the talk. I want to ask about the carbon dioxide emission during recycling, because I didn't see any slides where you mentioned about the emission, how much it is contributing in global warming during recycling.
Yeah, so if people didn't hear that, this is about what the emissions would be depending on what your recycling pathway is. I'm presuming you're going for mechanical recycling there. So we've done full environmental impact assessment, so LCA beyond carbon. I think it's really important to think about other ecotoxicological and water impacts beyond our laser focus on carbon. But what we know is that mechanical recycling is lower than virgin production, right? And is lower than a chemical recycling process or something like that. So chemical recycling really has a higher footprint. But when you look at the footprint of a multi-material construction, much of that footprint is captured in the rest of those materials. So a carbon fiber wind turbine blade, well, it's the carbon fiber that actually is a really big carbon sink. And so that, because you're recovering the fiber at end of life, then that compensates for the fact that you have a higher carbon process within that. But it comes back to your question, process energy, the energy we're putting into that is really quite important. Interestingly, I think the big push is to use renewable energy as the energy source to do mechanical recycling, which is a big push. And that, I think, makes it a lot more straightforward because you are using that perhaps at off-grid times as well to decrease the impact. But we do full LCAs on all of the stuff that we propose.
I think we have one last question over this way.
Yeah, so I have maybe a very naive assumption that when you want to create something with high performance, like carbon fiber, wind turbines or bicycles or something like this, you would need to use brand new materials rather than using recycled materials. Is this then the wrong viewpoint to have now? Are you saying you can really take the carbon fiber, break it down, and then build it back up and have the same performance as virgin materials?
Well, I think in the carbon fiber instance, the key is to maintain the quality of the carbon fiber, right? In a broader sense, there is a big push, especially in the automotive industry. Again, can't tell you who we're working with, on including recycled content in a lot of automotive parts. The key then is that you need to know what your strength is. So we do mechanical recycling in our lab with no loss of performance, right? But it requires absolute segregation. You really have to know what the contaminants are in those systems and what the additive sets are in your origin, right? So post-industrial recycle it instead of post-consumer. Then you can get that performance that you need for a high-end application.
Right. Thank you very much indeed. A great talk, and hopefully people can catch up over coffee as well. So our next talk is from Sepideh from Mechanical Engineering. Yes, excellent. And this is about biometric fluid-based surface patterning.
Hi everyone, happy to be here. Last time I attended one of these meetings was probably, I don't know, end of 2019 or beginning of 2020, and when it was in person. So almost 3 years I've been at Leeds, and I started a new experimental group focused on biomimetic functional interfaces. That hopefully I will talk a bit about why we are interested in biomimetic approaches and what kind of functional interfaces we are working on. And for the talk today, I will focus on some of the newer work that we are doing, learning from nature and trying to use it as a tool for patterning materials and fabrication, develop new fabrication techniques. So just to a brief introduction to what I'm interested in general. When I talk about functional interfaces, this can be different types of interfaces, soft interfaces, and we are generally interested in cleaning applications. So most of the research is sort of motivated by different cleaning applications. And we work on classic systems where the cleaning is done mainly by surfactants and self-assemblies of surfactant systems. So these are more traditional ways of cleaning, but also on less conventional cleaning methodologies where we use fluid interfaces and trying to minimize the amount of chemicals that we use for cleaning surfaces which are contaminated by different sort of nanoscale or all the way to microscopic colloidal systems. And what I'm going to talk today about is how we can create surfaces which have these anti-fouling or anti-stain or self-cleaning properties that go one step further and basically inhibit contamination and growth of contamination on the surface in the first place, so that we then need to consume less energy and use less chemicals for cleaning them. So I'm sure everyone is familiar with the biomimetic approach, but just a few words that helps us think a bit better about at least what I think about biomimetic approach. It builds upon inspirations from biological successful survival principles, and this is an important aspect that I'm going to come back to guide discovery research towards development of sustainable functional materials, methods, and solutions. So when we talk about successful survival principles in biological and natural systems, it's very different from the survival principles of human beings. So it's not how we get the best product and the best functionality in the fastest way. When in nature normally is what works the best considering the circumstances and how we can think about sustainability and how it works the best in the environment where the biological system actually is and is functioning in. So there are at least 3 research areas in biomimetic approach. There's the observation, discovery, and basic research and imitation. And while engineering has been mostly focused on the imitation, we are interested in all the 3 steps of the process. And when I was talking about nature's approach to best and the survival principles of nature, there's this nice article by Julian Benson that was published in 2002, which is called The Survival of the Cheapest. And it says that in his engineering, use of materials and energy, man lets design take second place, whereas nature treats material as expensive as design with apparent care and attention to details. This results in durable materials and cheap structures that are easy to recycle under ambient conditions. So there is the whole process that needs to be taken into account when you think about biomimetics. It's not only what is the functionality of the material, but it gives also good hints how we think about what type of materials are used and what type of methodologies and fabrication tools have been used probably by nature to create that kind of materials, and especially when we're talking about materials which are available in nature in larger quantities. And the quality of the picture is probably not good enough for this massive screen, but when looking at natural systems for inspiration, we are interested on the two sides of this tree of life diagram. On the left side, we are interested in insects, and on the right side, there are plants. And why the two? So plants, they are very impressive in terms of quantity. They occupy, there's an estimation that says that they occupy around 250 million square kilometers on Earth, which is around 50% of the surface area of Earth. On the other side, insects are definitely more impressive in terms of the quantity of the material that's available, but in terms of the designs, diversity of the designs, they constitute around 80% of the total number of species of all living matter on Earth. So it's basically a massive catalog. Insects gives us a massive catalog where we can go around and choose the designs, while plants we can go back and see what kind of materials are actually available to us to use. And so for the context of this talk, I'm going to focus on functionality and biomimetic approaches which are around water handling. And why this is important is just that in nature, most of the time, water is the source of contamination, and it reduces the functionality of many different species. So this is an image of dew formation in the morning, a cold morning on plants and insects, and you see that the water doesn't actually wet any of these surfaces. There's lots of humidity available in the system, in the environment, and it is inevitable that it's going to nucleate on these surfaces and it's going to grow condensation. But it's important that it doesn't wet the surfaces to reduce the functionality. So the functionality that we are interested in, and in the context of my talk, is superhydrophobicity. And the way we characterize it is if you put a water droplet on most of mankind's surfaces which are not functionalized, it most probably is going to wet the surface. And we typically measure a contact angle for that water droplet on the surface. If it's smaller than 90 degrees, we call it the hydrophilic surface. If it's larger than 90 degrees, we call it hydrophobic. But the functionalities that are around self-cleaning and anti-stain functionalities, they require superhydrophobicity, where the contact angle is at least larger than 150 degrees. But that's not enough. That's only in static conditions. If you're thinking about self-cleaning and anti-stain materials, you need also to think about dynamic conditions. And this means that small perturbation, mechanical perturbation, should make the droplet fall off the surface, and this then enhances the self-cleaning process that I'm going to come back to shortly. So why are we interested in superhydrophobicity? Because it helps with anti-wetting, anti-frost, anti-icing surfaces, anti-fog. So there's a whole range of material functionalities which are linked to superhydrophobicity, and they can also cause create lower friction in materials. But what we are specifically interested in here is how can we create anti-stain, anti-fouling, and self-cleaning properties. So there's this term self-cleaning was probably first introduced in some of the studies directed by Bartlett and co-workers, where they looked at one of the most important examples, or the best known examples of self-cleaning and superhydrophobicity, which is the now called the sacred lotus. But it's basically the plant, Naluma lucifera, which has this hierarchical structure on the surface. And what this nice article discusses is that when you put contamination on these kind of surfaces, first of all, because of this nanoscale and hierarchical and especially nanoscale surface roughness, the contact area between the contamination and the surface is substantially reduced, which means that the adhesion energy force is reduced. But at the same time, when water lands on these kind of surfaces, because of this superhydrophobicity, it creates droplets rather than wetting the entire surface. And then by small motion of the leaf, these water droplets can roll over, and when rolling over the surface, they can collect the contamination and clean the surface. So this is where the self-cleaning comes from. And they did this interesting experiments where they contaminated the surfaces with artificial dust, and then they created artificial rain over the surface. And they measured the number of particles which remained on the surface. So there were two groups. On the left, you have the group where there were more particles left on the surface. On the right, the surfaces were cleaned after the artificial rain. And when looking at the surfaces under an electron microscope, what they found out is that the surfaces which were cleaner, much better, were all the surfaces which had these hierarchical micro and nano structures on the surface. So how do we engineer superhydrophobic surfaces based on these kind of understanding? At this point, we know that what we need is structured surfaces. We cannot do this. There's only up to a certain limit you can create superhydrophobicity on super smooth surfaces. So we need surface roughness in the first place, but if the surface roughness is created in hydrophilic material, there's a chance that water actually infiltrates within these pores and gets stuck within those pores, and the self-cleaning process at this point is lost. So what we need, if we need the self-cleaning process and small tilting angle to create these, to lead to this self-cleaning process, is not only the micro and nano pattern surfaces, but also hydrophobic materials to be able to make the water droplet sit on top of these and basically on a very stable air cushion which is trapped in these structures. So at this point, what we know is that we need to have the right chemistry and have the right physical properties, the physical topographies on the surface to be able to have these kind of materials. And we are advanced enough in terms of micro and nano fabrication that we can create all kind of physical topographies. The issue here with most of the conventional micro and nano fabrication techniques is that these are all top-down approaches, and they're limited with scalability, and of course are very costly. So again, going back to biomimetic approaches, the sacred lotus leaves, the dimensions are order of meters. Can we use these kind of conventional techniques to create that kind of material? And the other issue with these kind of approaches is that we cannot control the chemistry because they are developed for certain type of materials. And then more recently, there are newer approaches which are bottom-up approaches where we grow structures on the surface, and there are vapor deposition, for example, methods. But here the question is, what is the right material and what's the right design that we can use to create the best and most sustainable, let's say, self-cleaning materials. And this is where we can go back to the biomimetic approach again. So if we look at the leaves of the sacred lotus, there are these hierarchical structures, beautiful nanostructures on the surface. On the other side of that graph that I showed you, the tree of life, we have very similar properties on insect wings. They are super hydrophobic and they have these self-cleaning properties. And again, if you look at the surfaces, they have similar kind of nanostructures which are high aspect ratio patterns and features. So we already knew that we need these kind of structures. What else can we learn from these two groups when we're comparing them? If you look at the chemistry, and I'm not a chemist, but if you look at the chemistry of the two materials, these are all waxy materials, and you see loads of alkane groups, long chain carbon alkanes inside, alcohols, fatty alcohols, secondary and primary alcohols. So if you compare the two very different materials, you see that in terms of chemistry, they're actually quite close. And in terms of the physical topography, again, they're quite close, which means that if we want to create functional, at least biomimetic functional self-cleaning material, the first thing, can we actually use these kind of hydrophobic waxes, reuse them, and create micro and nano structures? So what we try to do, and from especially all the research in 1960s and 70s on plants, we know that the structures which are on the plant leaves are most probably crystalline structures of these waxes. So what we try to do is to collect a sort of variety of different waxes which are available from plant-based, except for beeswax in this diagram, and look at their hydrophobicity and wetting properties. So you're looking at the contact angle measurements on a smooth surface of these waxes, and you see that already most of the values, they're between 90 to 100, 120 maximum degree, which means that we are already starting with a hydrophobic material, so good in terms of chemistry. But what about the physical topography? So these waxes at room temperature, they're solid. If you melt them and recrystallize them, by cooling, what you get is a rather smooth surface. So you have some sort of wrinkles on the surface. The scale bar is 10 micron in this graph. But if you look at the contact angle, it's around 100, maximum 110 degrees. If you dissolve them in a solvent this time and evaporate the solvent, you get beautiful crystals and surface roughness on the surface that gives a much higher contact angle. So you're looking at the, again, the scale bar applies to both images. So these are like micro roses, which are around 5 to 10 micron in diameter. And there was, from the previous research on plant leaves at least, we knew that these crystals, obviously they are correlated, their structure is correlated with the chemistry, but can we stick to the same chemistry but change the shape of these crystals and the surface topography, at least at microscale, hundreds of nanometer and microscale, which is then can be translated into wetting functionalities. So, how am I doing this time? Okay, so I'm going to skip this slide, but in terms of what kind of surface structure you can get, if we start from the left side of the diagram, you're looking at the graph that I showed you before. This is when we use solvents that evaporate really slowly. And so the 0% is 0% of acetone in the entire solution. While when we move to the right side of the diagram, we get structures which are more open. So we get smaller structures and then more opening that can then keep more air inside. So if you look at the wetting properties of these kind of crystals, you see that on the right side, as we have more acetone, so faster crystallization, we get much higher static contact angles, and at the same time, we get very small sliding angles. So we can create surfaces which have this lotus effect, and they have this self-cleaning superhydrophobicity. Using the same exact material and the same exact way, wax, by just changing the rate of evaporation and the solvent, we can then make surfaces which are still hydrophobic, but this time they don't have that self-cleaning and slippery behavior. And in fact, they're very sticky, so they can hold on to the water droplet if you pull it away. So basically, you can, just by changing the crystallization, the environmental condition that controls the crystallization and the rate of crystallization, you can change these micro and nanostructures without changing the wax. And then, obviously, you can change the wax, and the chemistry is going to give you a variety of different crystalline structures. So again, you can mix the waxes, you can mix solvents, and get a variety of different kinds of surfaces. So most of the surfaces that are created by using fast evaporating solvents normally give this higher water contact angle and slippery behavior and self-cleaning behavior. So I'm going to leave that slide, but just to say that when thinking about the waxes are good sustainable material, but there's all these issues of sustainability when you think about extraction of the waxes and the solvents that you're using. So there's still all those open questions around the sustainability of the process that we use. Otherwise, the fabrication technique is quite fast and gives good functionality down the road. Thank you.
Thank you. A really lovely talk. Have we got any questions?
I have a question.
Yes, question.
The Young Laplace equation, which has been used for macroscopic surfaces, can it be used for microscopic, nanoscopic materials?
I would say it depends on what type of functionality you're looking at. If you're just thinking about the self-cleaning, you can always use the equation. And It's just that when you think about self-cleaning, for example, most of the rolling dynamics, it comes from the pinning and the depinning from the surface. So at that stage, even if the Lang-Laplace equation gives you a certain fixed value, it's the surface structure that's going to bound you. So certain structures might enhance pinning and then they don't do too well with the self-cleaning, I would say.
Okay.
Yeah, Rick.
Is there much difference in crystallinity, size of crystallites for the different evaporation rates?
Yeah, very good question. I see that phase in the audience. We are looking at the crystal structure, and interestingly, it doesn't seem too different. So even the smooth surfaces that you have, be it just cooling the material, are very similar in terms of the crystallinity to the rough surfaces. It's just that it seems like the roughness, it comes from much larger scale aggregation. So these are all hundreds of nanometer and microscopic aggregations, secondary nucleation of the crystals that create these kind of larger structures, rather than smaller scale. Then for some of the materials, yeah, okay, the solvent also changes the crystal structure.
Thank you.
I think there's a final question over. Yeah, thank you.
Thank you. That was a really fascinating talk. I wondered if you could say a little bit about nature's ability to be adaptable to seasonal changes in terms of their super hydrophobicity, and how, what are the experimental challenges for achieving that kind of biomimicry?
So there's the seasonality, but there's also age that does come up in these kind of materials. We do work, so there's definitely we are working with museums to look at the samples which are available also in time, to look back, but also from different regions, which have actually different climates, to see if there are different patterns which are appearing in materials. But in plant leaves, for example, if you look at the age, also the structures, they change. So they become mature sort of at later ages. Insects, I don't know about that, but seasonality, they do not really change in different seasons because they don't have this capacity at the end to change. But most of the time, they're designed for that environment that they've been designed. So it's like extreme environments. You wouldn't have too much probably water content. It's a bit drier, while then there are more wet environments, yeah.
Okay. Thank you very much. A fascinating talk, and it's fascinating to see what nature, I think, can do for us. So thank you very much indeed.
Our first speaker of session 2 is Professor Themis Prodromakis from the University of Edinburgh, on a talk with Memristive Technologies from functional oxides to AI on chip. Thank you.
Thank you very much, and thanks to the organizers for extending an invitation. I'll be talking about functional oxides, talking a little bit more about what functional oxides can also do for emerging electronic technologies, also known as Memristive Technologies nowadays, and how this could also provide a new pathway for embedding AI on chips. A brief outline of the talk, go through the motivation, why we're actually doing what we're doing, what's the challenges that we're facing in modern electronics and AI, a bit more on what memristivs are and the fundamentals of them, and some application examples. So first of all, everyone is aware, how many are, by the way, here are engineers? Are there any engineers in here? Okay, there's at least some engineers. So starting with electronics evolution, everyone is familiar with Moore's law, which for over the past 7 decades, we've been doubling the number of transistors roughly every 2 years, every 1.5 years. And that has really led to the evolution of modern electronics. But what's important, last year we celebrated, beginning of this year, the 75th anniversary of the transistor. And what we should remember is that we've been computing. Moore's law has not just been around because of transistors, but we've been using all sorts of different switches for computing, electromechanical switches, relays, vacuum tubes, then transistors, and of course the integrated circuit that gave Kilby his Nobel Prize. But it's been over 120 years that we've been following this trend. So we are really in the pursuit of the next switch. And many people in the audience may know who Feynman is, but he gave this famous talk, is kind of the apostle of nanotechnologies, back in the 70s and the 60s, where he said that there is plenty of room at the bottom, but his prophecy has been partially fulfilled. Partially because, yes, we do have some amazing nanoscale, nanofabrication capabilities that we're using, some of which are actually in the Bragg Centre as well. But at the same time, as we start using those technologies, we're hitting some physical limits at the bottom. This is an interesting paper that came from Miranda et al., where they show that as you're going to deep submicron technologies, the transition from zeros to ones, the transition of your switch is not as smooth. And you start having, like these distributions because of the, you could see how the electrical potential profiles through the random fluctuations of dopants in materials start becoming very, very critical because you are in dimensions that are comparable to a few atoms. I'll skip this one, could return back to this. And on top of everything else, we've been hearing from industry that the end of Moore's law is here because it's becoming financially not sustainable to continue with scaling in deep submicron technologies. Now, AI also came into the mix and made everything worse. On one side, we see on the left-hand side that there's been over, nowadays, 200 billion interconnected devices. Our AI is as good as our access to our data, and therefore we need more of those devices, our IoT devices. But that has a consequence that we haven't considered, that just in 3 years from now, 2 years from now, we will be consuming about a fifth of global electricity simply for handling data, which is astonishing. And we do have to do something about this. So everyone's been talking, what's the big engineering challenge, which is how do we go from a von Neumann to a non-von Neumann computing architecture? How do we address the issue that the fundamental design of separation between memory and processing units and what are the challenges that this is imposing on computation and the energy consumption required? And someone could actually look at getting inspiration from nature. Nature has evolved to deal with this type of problems, like over many millions of years, and to do that in a very efficient way. So if I want to ask my students, who do you think could actually win? Which one is better if you were to compare a human brain and a supercomputer? They all, of course, start saying the human brain. But in reality, there is no particular solution to this question. It's a tricky question because it depends what is the type of problem that you're trying to solve. If you're trying to solve a problem that has a specific algorithmic solution, of course, a computer would do a great job in doing that. But if you're trying to navigate or drive a car or do something that requires a sort of approximate computing, obviously we're much better equipped than that. But if you were to do a fair comparison between the two, or an abstract as engineers would say, you look at computing, there's loads of parallelism as opposed to centralized sequential execution of routines. In terms of processing, we're using very slow, simple, however we use many synapses and neurons in the trillions in our brain. We're using on the other side very fast and complex components, but even if a few transistors actually fail, we do have an issue. Where on the other side, we are also allowing for a robust and graceful degradation. So we lose synaptic connections and neurons, like thousands of those every day. Yet we're still able to perform reliably. So how comes Memristive Technologies come into the mix, and what does this have to do with the Bragg Exchange, and with materials. So memristor is short for memory resistor. The term was coined up from Leon Chua, the chap that you see here on the left-hand side, who back in the 70s, he postulated the existence purely from a theoretical symmetry argument point of view. He said there should be a component that could link charge with flux, as, for example, we have resistors linking voltage with current. And simply by looking at the equations, he said this component should behave as the signatures that you see on the bottom, where you have a pinch hysteresis loop in the current voltage domain. So effectively, you have your stimuli, which is voltage, and the current, the maxima, being out of phase. The success came many years after that, almost 40 years afterwards, when the chap on the right-hand side, Stanley Williams, who was leading a team at Hewlett-Packard, was working on 2 terminal memory technologies based on metal oxide systems like titanium oxide in this particular case. And his success was that with his group, he managed to correlate the characteristics of these missing, link, if you like, with charge and flux, missing component, with the devices that he was measuring. And he called it, he published a nice paper in Nature. He said, we found the missing memristor. In reality, there's been a lot more researchers been working in the same sort of remit for many, many decades, even before Leon Chua postulated the existence of this. And as with any emerging technology, I see people already recognizing, they start laughing. There is loads of excitement, whether it's graphene, whether it's memristors, loads of excitement in the beginning, but reality kicks in. And, but with a lot of good engineering practices, we're able to utilize some of these technologies for some good. And I can actually point to you all the points and why this is important for memristors. Functionality, you're not only able to store zeros and ones, you can actually truly store analog memory states per single devices. Footprint, state-of-art devices by Shia and Tal at Amherst have shown that have been demonstrated down to 2 by 2 nanometers, well below CMOS scaling at the moment. Power, you only require picojoules of energy to toggle between different memory states. Speed, you can do that with picoseconds of pulses, but guess what? No surprise, variability is horrendous at these scales. However, we're not reinventing the wheel. These are problems that we've seen in the electronics community with different types of memories, and there are ways to push your system to take particular memory states and do a compromise. And of course, whenever something doesn't work, people would always argue that it's either good as a sensor or for neuromorphic computing. And this is indeed the case with memristors as well. So people have their hopes really high that this will solve, like all the challenges with the AI, as I mentioned before. I do believe, though, we do have a chance in doing that, and I hope I convince you by the end of this talk. So looking at bio-inspired memories, Eric Kandel got his Nobel Prize in Physiology back in 2000 because he managed to demonstrate that memory is transcribed in synapses, which is, again, an abstract overview of an engineer. Very simplistic. You have 2 terminals. You have a presynaptic neuron and postsynaptic terminal that links to another neuron. And in between, you actually have a synaptic cleft in which neurotransmitters diffuse. And that's what transcribes memory in biological systems. When you look at that with an engineering perspective, it looks rather similar to this. I hope you would agree with me, in an abstract kind of way, in a phenomenological way, where you still have 2 terminals, a top and a bottom electrode, and which is denoted here as blue with platinum. This is a high-resolution stem of a cross-section of one of our memristors. And in between, you have that barrier, which is nothing more in this case by titanium oxide material, thin film that has been used, as the synaptic cleft, if you like. So that looks rather similar to that, and you have the diffusion of oxygen vacancies, but even titanium interstitials in this case, which transcribes different memory states. Now, memristors covered a very broad range of memory technology families, if you like. So there are valence chain memories where you have oxygen vacancies, for example, moving up and down a resistive RAM. You have electrochemical metallization cells, where you have a diffusive metal, which diffuses within an active host. And you also have phase change memories, where you toggle the crystallinity of the material that is sandwiched between those two electrodes. We published this commentary a while ago that describes the pros and cons of different technologies. And again, there's no one size fits them all, because phase change memories, although they are pretty reliable, we do understand the physical mechanisms very, very well. They suffer from relatively high energy consumption, and they do not perform so well as, for example, the valence change memories in terms of analog computation. On the other side, VCM type of memory devices, they really suffer from the variability. So let's look at the materials. Almost everything switches, I can guarantee you this. I've seen actually people demonstrating even memristors made out of plants, of blood, all sorts of different things. Inertia is fundamental in nature, in everything that we do. So if you look at that table, everything that's color-coded, and that's already a few years old, there are papers in the literature that describe a memristor being made with these sort of materials. In my group specifically, we focus with these particular materials that are in the square. So with titanium oxide, niobium oxide, but specifically hafnium and tantalum oxide, but also silicon oxide. Why? Because we want to really utilize this together with CMOS technologies, and these materials you also could find them for free in as high-K dielectrics that have been used in deep submicron technology. So it's important to have this interoperability. How devices look like, which topologies? There is, again, a variety of different topologies, still two terminals, but you can have them in cross points, in plug points, in vias, for example, or vertical layers, which allow not just for the integration on back end of line, but also integration in 3 dimensions of these technologies. And all they have very different manufacturing implications. So let me show you some of these devices and how they look like. This is the AFM microphotograph that you see on the left-hand side is about 1 by 1 micrometer. So you have 1,024 devices in there. Every little knot that you see, every little square that you see in this carpet sort of like structure, it's one device. So you have a cross-point device. And one of the biggest challenges that me and my group, thanks to funding that we have from EPSFC as a program grant called Forte, which is a collaborative program with Imperial College and Manchester University, is not only to develop the materials, the different functional oxides, but integrate them in collaboration with TSMC at full 8-inch wafers on the back end of line. So we integrate them on top of standard CMOS wafers that we procure from them, and we allow different groups to come up with a number of different designs. So effectively running like a broker, where we allow electronic designers to develop their circuits, send the circuits to us, we assemble them, and we return the different chipsets. Not an easy thing to do, but it has loads of perks and loads of fun moments. And this is something that we just received last month, one of the proud moments and milestones in our program grant, where it's a 1 million, 1 megabit sort of elements of memristors, which are sitting here in between, which have all the instrumentation on chip to allow us to program these devices as we wish. So it's a characterization array, but it has also different applications that we're trying to exploit with it. So how do they look like? How do they operate? These metal oxide systems that we develop have shown that they can even support up to 7 bits of memory states per single device. So we're talking of hundreds of discernible memory states in a single nanometer scale device. This is why a lot of people say you can get more for less. So more functionality for less power, less chip real estate overall. And if you look why this is important, is because you can also store them in a non-volatile fashion, which means you do not have to burn any energy to sustain the memory state that you've seen. These are just a few randomly neighboring memory states selected, and you could see retention characteristics for over 8 hours. which is really great. When you program them, you can send a number of different voltage pulses. So you could see you could program the devices. Effectively, they act like tunable resistors, which is really great because you can use them in different circuits for tuning their performance. And as I've mentioned, it only requires picojoules of energy to go from one state to the other. But in the early days of these technologies, there's been quite a lot of challenges with how we use the technologies, which is the so-called time voltage dilemma. Just follow my thoughts here. So if you start from an initial memory state, resistance, so you see here the transient response of one of these devices, and you want to reach to a final memory state, you have loads of different ways to do that. Either by using a train of pulses with a fixed amplitude and a fixed pulse width, in this case 100 nanoseconds, and you go into these steps, or provide more the same energy, but instead of just cranking up the amplitude, like you can have a wider pulse or increase the amplitude. And this has caused a lot of challenges in the early days because people were finding it very, very difficult because of this history dependence in programming and controlling these devices. So where others had seen a challenge in using the technology, we actually saw an opportunity. And the opportunity was that these devices, the fact that they act as an integrator, they allow you to do some very exciting signal processing at the device, at the edge. So let me show you a couple of examples on how this could work. A couple of examples that span across sensing, recognition, learning, and reasoning. So first of all, how you can employ the device physics for doing compression of data at the device front. So how do you switch the devices? They have two different switching thresholds. Below this switching threshold, nothing happens. So that's great. As you could see here, there are the switching thresholds in positive and negative polarities. Nothing happens in terms of the memory states of the devices. If you go above this hard breakdown switching threshold, you have irreversible switching, and that's also something that has confused the community because they were seeing these big, nice butterfly sort of pinch hysteresis loops, and they thought we have a memristor, but effectively the only thing that they had was a damaged device. Okay. So we have to be really careful about this. So this is where all the magic happens, where you have reversible switching, and you observe these changes in analog memory states. So in that case, we came across, we were talking to colleagues from electrophysiology, where they were doing neural interfaces, and one of the biggest challenges they have is how they can do in parallel computation on spiking events that look like the ones that you see on the right-hand side on the screen. And effectively what they do, they have systems that are continuously on. They burn a lot of power to process these very rich signals. In our case, what we've done, we simply pass those signals through the devices and using this threshold and integration capability, and effectively every spiking event, as it was exceeding the switching threshold of the device, it will passively change the resistance of the device. So you could go back without oversampling your electronic systems. You could go back and say how much activity has been here, and you can do spike detection. So these are the spikes. The corresponding change in resistance effectively denotes that you have a spiking event, so you can do spike detection. But the beauty of this is that you can also do spike sorting. Spike sorting meaning that you can, instead of doing template matching, which is computationally very expensive, you could simply look at the overall change in resistance in your device and figure out what sort of spiking event has actually biased your devices. So this is just one example. A second example has to do with Bayesian inference, one of the most computationally heavy, one of the most, if you like, heavy operations in circuits is multiplication. In this case, you simply use Kirchhoff's law. You have this crossbar array, and you could use the weights stored in your array to sum currents in lines and rows to do vector matrix vector multiplication in an extremely energy efficient way, which is particularly useful for robotics, for different AI type of applications. Third example has to do with developing new electronics design paradigms. So some of my students had this brilliant idea, let's get a standard textbook of electronics and start adding memristors into the mix. So here's a great example. If you have a digital gate, and this is a transfer characteristic of a digital gate, what will happen if you add those analog devices in there? Effectively, you skew the transfer function, the transfer characteristics of your gate, and you turn it into an analog gate, something that can actually compute analog values, but at the cost of digital. Bear in mind that we are nowadays using digital technologies mainly because of the energy efficiency reasons and the scaling. But these technologies effectively allow us to go back in using analog and doing signal processing in analog domain, which is really great because we sense our environment with analog signals. We process continuously analog signals. And of course, you have the ability to reconfigure this on the fly as you wish by changing the weights of the devices. Another example is in silico implementation of biological learning rules. I'm not going to bother you so much with this, but effectively you can have artificial neural networks created with these devices and store the weights in these functional oxide devices that link those neurons. This is just a winner-take-all example where we've demonstrated for the first time unsupervised learning in probabilistic computing. And last but not least, if you have a device that more or less speaks the same language with biology, why don't you use that technology to interface to biology as well? And this is an example that was a key milestone for a European project that we had with different colleagues from Padova and the Institute of Neuroinformatics in Zurich, where for the very first time we have linked a real intelligence, real biological intelligence, which was a rat's brain, with artificial intelligence. So artificial neurons fabricated with silicon technologies via the use of memristors. So effectively you have a real brain with an artificial brain operating in real time bidirectionally. I know it's scary, but it's done. It's done at a single sort of channel kind of proof of concept, and a lot of people feel that, you know, what does that really mean for applications? Well, it opens a lot of different prospects because that shows that artificial neural networks can actually operate concurrently with biological in real time. Imagine people suffering, for example, from Alzheimer's, that they may have dysfunctional parts of the brain sometime in the future, potentially replacing those parts of the brain with this sort of memristor chipsets. Of course, there's so many ethical considerations and so many different, you know, like aspects that come up that one has to consider, but it's really fascinating. So in summary, I think the opportunities landscape is immense, and a way to represent this and the role, the fundamental role that materials play into this is this policy paper that we put together with colleagues on behalf of the Royal Academy. We've tried to explain in simple terms what's the AI taxonomy, because everyone is talking about AI these days, but there's loads of confusion. What are the different layers of abstraction? So there is 5 fundamental layers. There is a physical instantiation, and that's where the materials come in. There is the functional, the computational, the semantics, and the agency. And just to put it in simple terms, something that my kids would understand, we've used Lego analogies, Lego blocks. So in the physical layer, the materials that you're using for fabricating, for example, memristors or different hardware implementations, think of Lego analogies. What sort of plastic, what sort of materials were you using for fabricating those Lego blocks? It defines the attributes of those Lego blocks. On the functional layer, which is above that, think of the different shapes that you can actually make those Lego blocks. At the computational layer, you start assembling a few of those Lego blocks together to define some functionality. So for example, developing the wing for a plane. And of course, at the semantic layer, you start putting more of those pieces together for making a plane. Last but not least, the agency layer. is imagine of a whole airport made out of Legos, and you also have the human in the loop interacting with that. And I know that we kind of think that AI is really far from what we do in terms of material science, but it's so fundamental because it underpins all of these technological developments. There is loads of different applications that are being demonstrated with these technologies, ranging, of course, from data storage, next generation of memory technologies. This is not science fiction. It sounds very low TRL, but it's not. Intel is already using Memristive Technologies in the 3DX point server solutions that they have. TSMC is already integrating these technologies in dips of micron in 22 and 40 nanometer technologies. So it's coming, it's here. Of course, in different, like bio-inspired electronics for health monitoring, and for image processing, pattern recognition, data clustering, and so forth. A last example, which is very exciting, is that because you're using ions and not electrons per se, these technologies are rather immune to radiation. So it opens very exciting prospects for radiation-hard electronics, which a lot of people think that these are only useful for space exploration or putting stuff in orbit. Well, not really, not just that. There is this review paper we published last year, the year before, in Nature Electronics that covers all those different applications and what are the benefits of these technologies in terms of radiation hardness. So with that, I'd like to finish my talk. Thanks again to the organizers and all of you for bearing with me whilst I've gone a little bit off topic and shown what is the impact of these technologies in modern electronics. And of course, many, many thanks to my group for coordinating all of this technological development. There's people up there that you see who come with a background of material science, electron device engineers, circuits and systems and computation. And of course, without I should definitely thank all the funders for supporting all the work that I've presented here today. Thank you so much.
Thank you, very interesting talk. We have time for a couple of questions. Yep.
Hi, thanks for a fascinating talk. When you were speaking about connecting the biological brain and your memristive brain, and you said you could see it working or something, I mean, what does working mean? Does it mean you could see signals going back and forth, or could you observe it doing something like responding to a stimulus or something like that?
Indeed. So we had, first of all, we did it all geographically distributed. This was a cool example because we're trying to figure out how we can continue collaboration throughout the pandemic. All right. And we did everything via the internet. So we had real neurons cultured on Petri dish. So it was a rat's brain with multi-transistor arrays picking up the signals from the real neurons, interfacing and getting that transduced via memristive synapses at Southampton. At that time, I was at Southampton with my group, and then using that for stimulating artificial neurons made out of silicon chips, 180 nanometer CMOS technologies, which were located at the Institute of Neuroinformatics in Zurich. Then we were getting those events stimulating the weights of memristive synapses, which were in turn stimulating the real neurons back. So it was a bidirectional real-time communication. What I'm not saying here is what we did to address the latencies because of the internet latencies that we had, because you have to have plasticity events occurring at the same time. But we've done some tricks to address that.
Thank you.
I'm happy to talk more about this over the coffee break. There's been a lot of coverage on that. I think the first 2 days they came out, it was over 40,000 downloads of the paper, because it's the first time that real with artificial intelligence was operating concurrently.
Hi, thanks very much for the nice talk. Can you say a word about the material science of these systems? So if I think of TiO2, and you talked about ion transport, there's ions one way, electrons another way. I mean, is this crystalline oriented? Can you tell us a little bit about?
So there are
TiO2?
examples.
Yeah.
This is why I've added this particular one here, because there is different mechanisms that coexist. So in the case of titanium oxide, there is oxygen vacancies that are being displaced, and we've actually done some EELS analysis with higher resolution STEM to show that it's not just oxygen vacancies. We've shown that titanium interstitials move as well. Okay, and it depends on what sort of material systems you use.
It's amorphous or crystalline?
In this particular case, it was amorphous. However, this is a very, very good point, because if we take the titanium oxide system, here I show effectively 3 distinct switching mechanisms. I've shown the displacement of ionic species or oxygen vacancies. Here I show the diffusion of an active material into a host, and this has to do with the phase change. In reality, however, if, let's say, you have a titanium oxide system, you have redox reactions occurring. You have the displacement of oxygen vacancies, so you are reducing effectively locally. That's so immediately you are also changing the phases of your material, but at the same time, you're also moving titanium interstitials. So really, in reality, all 3 kind of mechanisms coexist. And we had a paper with through synchrotron facility studies where we've shown that you can actually have rutile and orthorhombic phases appearing, which was completely unthinkable for us. We thought it was a mistake, but actually it's not, because the temperatures that are created, if you overswitch those devices locally, they are significant, they are substantial to have these sort of phase transformations.
Interesting, thank you.
Are there any more questions? No? Well, can you join me in thanking them again? So our next speaker is Dr. Joseph Barker from the School of Physics and Astronomy with a talk on ultra-fast spin currents and antiferromagnets. Thank you.
Lovely. Thank you. So it's lovely to be here. Let's see if I can go the right way. I think I'm in the middle of your deck. Good, thanks Andy. So this is me. We're just before the coffee break. Everyone looks a little bit sleepy, so I'm going to wake you all up with some hardcore physics, just for fun. So that was a wonderful introductory talk actually, because a lot of the problems that we aim to solve in my field are the same problems. Now the Memristive guys are a little bit ahead of us, but essentially spintronics is all about trying to create new low-energy devices for computers to create memristors, essentially, out of magnetic materials, and to do non-conventional computing. Today, I'm going to really focus on one specific topic. So this is ultra-fast spin currents and antiferromagnets. Now, I'm going to be very gentle to start with, because even in undergraduate physics, we don't teach more or less any magnetism. So I'm going to actually explain what an antiferromagnet is, which will hopefully help you all a lot. And then we'll get to some of the gory details later on, just for fun, just to show off, really. And most of the work here is from this preprint, which is now accepted into Nature Comms, which is always nice. So, other way. I should thank my lovely collaborators. So, a lot of the work here is actually driven by the experimentalists. So I'm a theoretician, and we'll see later in the talk about how we can develop quite sophisticated theories to understand these experiments. But the experiments are mostly done here in Cambridge by Chiara Cicciarelli's group and her PhD student Faran, who did most of the work. The samples are from Pisarev in Russia, and then Davide Bossini helped with a lot of the characterization of the materials. Now, interestingly enough, this is Chiara at the Bragg Exchange last year, giving a talk where in her conclusion slide, she said, this is the latest work that we're doing, and this is what I'm now going to talk about today. So I should also thank the Bragg Centre for continuing to support our work and for continuing to give us space to talk to you about it. It's quite nice to kind of have an annual cadence update of what we're doing. Right, so ferromagnets and antiferromagnets. Now, antiferromagnets are the really hot topic at the moment in our field, and there's some very good reasons for this. But first of all, we need to understand the differences between them. So if we look at a ferromagnet, one of the really important points here is that, does this have a laser pointer? I'm going the wrong way again. Can you help me on this? That's not even one of my slides. Right. What are you doing? Definitely before the coffee break. This has gone miles away. Yeah, just start from there. So in a ferromagnet, we have these stray field lines. Just imagine you've got a bar magnet and you've got these stray field lines coming out. And if we zoom down to the atomic level, then basically on each atom we've got a little magnetic moment, and they more or less all point in the same direction. And that's what's giving these stray fields. Now, what's really good here is that these moments line up very well because of a very strong quantum mechanical interaction between them. So this means that ferromagnets are still magnets at room temperature, which is quite useful. We have gigahertz dynamics, so the kind of frequencies that these things move at are in the gigahertz regime. That's quite useful. Computers work in the gigahertz regime. But the problem with these stray fields is that that's what causes magnets to interact with each other. So if you want to put a bunch of magnets on the nanoscale on a chip together, they're all interacting with each other, which isn't necessarily a good thing, because if you want to make a memory device and you want to just flip one of these magnets upside down, all the magnets around it can feel that and will be influenced by it and may flip with it. So this is a big problem if you want to really make kind of nanoscale computing devices out of magnets. Magnets can be easily manipulated with a magnetic field, so this is one of the key ways that we can tune something. So in the old magnetic hard drives, which are still used in data centers, this is how we manipulate the magnets. That also means that they're easy to measure. We can see this magnetization, and so we can really determine the state of the magnet very easily. And most importantly, these ones stick to your fridge, okay? So this stray field couples to the metal on your fridge, and it sticks. Now, antiferromagnets are quite interesting in that they're still really strongly ordered. At the atomic layer, you've still got these magnetic moments, and they're still coupled really strongly through this quantum mechanical interaction, but they are anti-aligned. So each atom by atom, you've got one up, the next one's down, the next one's up. And really what that means is that you have no stray field. Because all of these tiny, tiny magnets point in opposite directions, all the fields cancel out. And so there's no stray field. And what this means, basically, is that it does not stick to your fridge. It just looks like some lump of metal or some insulator, and it won't stick to anything. So this means that it doesn't really interact very much with the outside world. It has a tiny, tiny response to external magnetic fields, and this means it's really difficult both to manipulate and to measure, because unless you can measure on the atomic scale, you're going to really struggle to have it. But of course, the lack of stray fields is fantastic if you want to put these next to each other on a device. So you could pack them in really, really tightly without any issues. The other interesting thing is that these naturally have a terahertz dynamic. So for quite complicated reasons, you get an order of magnitude faster dynamics in antiferromagnets. And all of this is not just kind of hocus pocus up in the air thing. So the field is really led by a guy called Thomas Jungwirth in Prague. And within about, he's a theoretician as well, interestingly enough, and within about 4 years of him discovering a new way to manipulate antiferromagnets, they actually built this room temperature memory device that just for fun he takes to conferences sometimes and he can plug into his laptop and he can show you it storing the different memory states. I think it was an 8-bit device or something like this. So, you know, this field has real legs. But what I want to talk about is how we can kind of see some of the terahertz effects that are going on here. So I'm going to start with a lot of simple pictures and try and be very gentle with everyone before we get to the research. So the devices essentially look like this. We have some chunk of magnet, normally quite a thin film, but it's not so important. And then we put a heavy metal on. So heavy metal means something like platinum, something with a large spin orbit coupling. And we're going to shoot a terahertz laser at the metal. And what this is going to do, it's going to heat up the electrons in the metal. They're going to get really, really hot and start shooting about all over the place inside the metal. And they're going to then collide with this interface with the magnet. And then this is going to drive a spin current. So electrons carry a quantum mechanical property called spin. And magnets intrinsically also include this spin variable. So you can get a current of spin. So instead of a charge current, you have a spin current. And then through a really beautiful piece of physics called the inverse spin Hall effect, you then actually get this spin current driving an electric current in this heavy metal, and that electric current then causes a terahertz emission. Because this whole process from shooting the laser to this terahertz pulse coming out, you're talking of the order of 1 to 2 picoseconds. This is a very, very fast event. So really, in this work that we did, we wanted to focus on the interface and understand a lot more about the interface between antiferromagnets and the metal and what's going on there. So let's just look at the interface in general. Let's just look in equilibrium. Let's not shoot any lasers. Let's just try and understand a little bit about what's going on. Essentially, you have an electron with some spin up. So spin normally comes in flavors, up and down. So you have a spin-up electron, which is just, for no particular reason, moving around in the metal, and it hits the interface. And what can happen is it can then create something called a magnon in the magnetic material and bounce off the interface, and its spin has been flipped. So it's taken some of its spin, and it's injected it into the magnetic material. This is why it's a spin current, because you're moving spin from the metal to the magnetic material. You don't need to worry too much about what a magnon is. This is a quasi-particle in a magnet that carries spin. Now, the opposite process is also happening. So magnons are just merrily moving around inside the magnet. They might hit this interface, and they will be destroyed. And in doing so, they will flip the spin of an electron that happened to be next to the interface at the same time. So actually, what is happening is you've got a spin current coming this way because of electrons hitting the interface, and you have a spin current going that way because of magnons hitting the interface. And in equilibrium, these cancel. There is no net current, and this is what you would expect at equilibrium. There should be no net currents. What happens when we shoot a laser? So we shoot the laser in, and we heat up a lot of electrons. So the laser doesn't really interact with the magnons at all. It only interacts with the electrons, and it makes them really, really, really hot. And this means the electrons move around a lot more, but it also means that there's a lot more electrons at higher energies compared to the magnons. So remember, we're talking about really, really, really short timescales. So the metal may have heated up by a couple of hundred Kelvin, but the magnons are still at their ambient room temperature. They haven't felt the temperature change yet, because it's through effects like this scattering at the interface that they will become thermalized. So what happens here then is that you will get a spin current increase in this direction, but the reverse process stays at the same equilibrium value. So this is how we get a net spin current. It's because we have a lot of hot electrons hitting the interface, but the number of magnons hitting the interface hasn't really changed. So we've broken the balance between these two processes. Okay, this is really the basics. This is true of putting any magnetic material here. So what Chiara did was quite interesting in that she took an antiferromagnet, because they're the hot topic, but she took a very particular family of antiferromagnets where these two materials, the potassium cobalt fluoride and the potassium nickel fluoride, they basically look exactly the same, apart from they've just got a tiny difference in their magnetic properties. So the crystal structure is the same, the magnetic structure is the same, but then there's just a very small change in their magnetic properties. And she wanted to see if this makes any difference to the signals that we get. So this is what a typical signal looks like. So as I said, it's about 2 picoseconds long, and this is just a terahertz transient that you can measure being emitted from the platinum. Now, if we have a look at the amplitude of that terahertz signal for these two different materials, and as a function of the ambient temperature, we see dramatically different behavior. So on the left, we have the potassium cobalt fluoride, and we see that it actually starts with a very low amplitude. It peaks around the nail temperature. So below the nail temperature, we have an antiferromagnet, but above the nail temperature, the antiferromagnet is too hot, and this quantum mechanical interaction breaks down, and we don't have an antiferromagnet anymore. But in the potassium nickel fluoride, we just get a continuous decrease in the amplitude up to the nail temperature. So these two materials that, on the face of it, look really, really, really similar, have actually remarkably different results. So we start thinking about this and trying to understand it, and try to understand the fundamental difference between them. And if we look at the dispersion of the magnons, so these quasi-particles that live within the magnet have a dispersion the same way that electrons or phonons have a dispersion. So this is basically a measurement of the energy of the particle as a function of its wave vector. And we see that in the potassium nickel fluoride, this looks like a very typical, normal antiferromagnet, a nice linear behavior. But it's actually got quite a small gap here at the bottom, okay? And this gap, it's about 0.1 terahertz. It's just a little bit bigger than a ferromagnet, for example. So when I talk about things having a terahertz dynamic, more or less I'm actually talking about the size of this gap. Whereas in the cobalt fluoride, we have a huge gap. It's 1.2 terahertz. Now, this is actually quite important, because what this is saying is that below this gap, there are no magnons. They simply do not exist. So if you have an electron coming in with some energy, but there is no magnon state that it could scatter into there, then you simply cannot get a spin current there, because you cannot have this process. The electron will hit the interface, but it cannot generate a magnon. It's completely forbidden. There are no magnon states there. So it stops a spin current from forming. And then the reverse case is also true. There are no magnons because there are no states there, so you also don't get the reverse spin current. So we believe that this gap is what is changing the behavior. And, you know, it completely makes sense. So here, as we go up in the colors, we're increasing the laser fluence. So we're giving the electrons more energy, such that more of them will be over this gap, and we do indeed get a larger signal. So there's more spin current. And also increasing the ambient temperature means that you have more electrons and magnons above this gap. So you can get some more spin current in that direction as well. So we want to understand this well, I want to understand it theoretically because I'm a theoretician. And it's all well and good looking at these diagrams and coming up with this hypothesis, but how do we really test it? Because this is a really complex non-equilibrium situation, right? This is not something that you can easily just kind of do a back-of-the-envelope calculation and say, yeah, that's about right. You know, you've got hot electrons flying around, your magnons are very cold. How are we going to look at this? So I turned to a paper by a couple of friends of mine where they'd studied something similar in the past, where they were looking at the same process but between metallic magnets and metals. So in our case, the antiferromagnets are insulators, so the electrons cannot pass into the material. Whereas in this case, they were considering how the electrons pass into the material. And all we essentially need to do is to do similar to what they did, but for an antiferromagnet and an insulator. It sounds very easy. and it wasn't too bad. So for anyone who actually interested in the details, essentially we have a Heisenberg model for the antiferromagnet, a Hubbard model for the platinum, and then we do SD coupling at the interface. So the electrons, we assume, are always thermalized. They thermalize very quickly, but we allow the magnons to have a non-equilibrium distribution, and we apply Fermi's golden rule. And I don't want to go into too many details, but I do want to point out that sometimes you have to do a little bit of maths in material science and, you know, get some answers out that way. And in the end, we get some very simple equations. So that was the complicated equation, and these are the simple equations. But what's really nice here is that each one of these equations, you can point more or less on that diagram and say what this equation is doing in that process. So up here, we've got the magnon dispersion, which includes the gap, for example. And then here, we've got an equation which describes the spin current. So one of them is the spin current in one direction, one is the spin current in the other direction. And then we've got the dynamics of the temperature of the electrons. We've got something called spin accumulation, which I'm not going to tell you about. And then we've got the population of the magnons within that distribution. So you end up with a really quite beautiful description, which you then just have to solve in time. And you get some nice pictures like this. So this is our temperature of our electrons going up, and we can see that as the temperature goes up, the net spin current is also spiking up, and it's all within about 2 picoseconds. And all the parameters in this model, it looks like you've got lots of different symbols there that need lots of different parameters, but actually most of them are quite well known, and we don't really have many fitting parameters in here, and yet we can reproduce the results on really quite a decent level. You know, my aim is never to actually reproduce the experiments perfectly, because often you don't really learn anything by doing that. And it's only in the differences between what you calculate theoretically and the experiments that you really start to learn what's going on. So really, I think from this we can say that the gap is the major factor here, and tuning that gap would allow you to tune the spin current. What I would say is that there's still some really interesting open questions. So in the ferromagnets, rather than the antiferromagnets, the gap is also very, very small, and you get this almost identical behavior once you've normalized the critical temperatures. The ferromagnets and the small gap antiferromagnet look almost exactly the same. And we're still trying to understand exactly why they should be so similar. I would imagine that they would have the same kind of rough behavior, but this kind of universal behavior I think is quite fascinating. So with that, we should move on to conclusions and hopefully some coffee soon. So I think it's really exciting, this kind of field of terahertz spin currents. Just being able to see how quickly things can happen in the antiferromagnets, I think, is really inspiring for the future devices that we hope to make. And I think what's really good here as well is to show how, despite the complication of what's going on in the experiment, you can actually boil it down to some fairly simple equations and really understand these complicated non-equilibrium effects and point to something and say, this is the physical source of what's going on there. Thank you very much.
Thanks, Joseph. Quickly move on to questions.
I have a couple of quick questions. The first one's very naive. I'm sure you correct me where I go wrong. So if I think about the practical aspects, the resolution of that device is limited by the width of the laser, I presume. But aren't we trying to pack more and more devices into a smaller and smaller volume? And isn't that some kind of limitation in terms of the practical use of this?
Yeah, so I think this particular device, we're not really imagining that we're going to build computers with a bunch of lasers in them. I mean, hammer accepted, right? But the purpose here is to be able to generate terahertz pulses, actually, which is a big industry in itself. So certainly with the ferromagnets now, they have devices that you can buy where you can generate broadband terahertz responses, and you can fill in that terahertz gap using spintronic devices, which you can't do with almost anything else. So possibly with the antiferromagnets, you can get an even broader band, or maybe you can get something peaked in the middle of that forbidden band. So yes, this particular device is probably not for computing, but fills actually quite a crucial role.
And then you have these two isostructural materials. Have you made a continuous series of solid solutions? And what happens when you substitute cobalt and nickel? You get the integration of those two effects, presumably.
Yeah, no, we haven't done that. So one of the unfortunate things is that the materials are made in Russia, and for funding agency reasons, we're not allowed to get any new ones. But yes, there are potential, lots of potential things to look at. So indeed, the changing of the nickel and the cobalt and substitution is a very interesting one. You do have to be a bit careful in general, because once you start choosing different elements, you might end up in different magnetic ground states, which then changes the physics quite a lot. So that's the next thing that we're studying theoretically, is to see how different magnetic ground states affect these terahertz pulses. So whether you have something that, instead of looking like a chessboard, you can have layered antiferromagnets, or you can have in-plane versus uniaxial, things like this.
Any other questions?
Now, these are the strongly correlated systems, is that right? The strong correlation effects, we had a XC, exchange correlation term in one of the slides. Do you take into account the strong correlation effects?
No, so most of the magnetic materials on this level can be modeled with a Heisenberg model. So you already assume that the exchange is very strong. So in principle, you can go down a level, do the first principle calculations to calculate the exchange constant, and then propagate that up to models of this scale. But we don't believe that the hot electrons are seriously affecting the exchange interaction.
Okay. The Hubbard gap, you mean the Hubbard gap, is that? Or the short chance gap?
So the gap at the bottom is basically the product of the exchange and the magnetocrystalline anisotropy. So indeed, if either of those are changed significantly, that will change the gap. And those two parameters change as a function of temperature. But I think you have to go to very, very high energies to start really changing the exchange interaction within the magnet.
Okay. Thank you.
If you join me in thanking Joseph again. Thank you.
All right, I think the moment everyone's been waiting for is coffee. I think we're running a little bit behind time, so I think we're going to cut the break down from 30 to 25 minutes. So if anyone would like to file out, what time are we on now? Back at 22? Back at 22. Thank you.
This is the start of the first sessions, which will be about nanotechnology. Welcome back from the break. And the first speaker will be Hendrik Dietz from Technical University of Munich. He's going to talk about fiber trapping and nanoparticles.
Okay, so hello everybody, it's a pleasure to be here. I'd like to talk about virus traps and other molecular machines of the future. First, I'm going to spend a few minutes, tell you what the general research interest is. So actually I'm going to use this. So the mission, or like the dream, let me put it this way, of my research group is to be able to build artificial molecular machines and devices that can accomplish user-defined tasks, much like we know it from natural molecular machines like proteins and enzymes. They can do it, but we don't want to look into nature. We want to build such things from scratch, and then, of course, make them do useful things. So the primary approach that we are pursuing is, in laboratories, we're trying to adapt the very same principles that nature uses to build up molecular structures, which is self-assembly and folding of heteropolymers for our own purposes. So we're studying how we can encode molecular structures in the sequences of biopolymers primarily. So in our sort of primary approach, we're primarily operating in the field of DNA nanotechnology and DNA origami. I'll tell you more about what that actually is. But we also do a little bit of de novo protein design. We're actually increasing that segment also. So let me start by introducing the field of programmable nanofabrication with DNA origami. So these are a couple of interesting words. So let me try to explain what it is. So you know that we can read DNA by DNA sequencing. We can also write DNA by DNA synthesis. And as a matter of fact, you can also build with DNA. So as a quick reminder, behind me you see a picture of a DNA double helix. This is the form in which most of our genomic material is stored in. A DNA double helix consists of two separate molecules, so-called DNA single strands, and if they have so-called if they have so-called complementary sequences, meaning they can satisfy a Watson-Crick base pairing rule, then these two single strands in solution, they will self-assemble and wrap around each other to form this kind of helical structure. Now, it turns out that in order to use, well, you can actually use DNA double helices to actually build up larger structures. I liken this to a form of weaving, but on molecular scale. So you can imagine that you wanted to build a fabric like this one here, which is basically a sheet of DNA double helices that are arranged in parallel, and that sheet has a certain contour. So let's say let's just assume you're capable of doing that. You can also envision that you might be able to stack multiple sheets on top of each other that have different contours, and then you can approximate customized three-dimensional shapes using DNA molecules. So the key element in order to do that is to create connections between DNA double helices at user-defined positions. And interesting enough, the DNA double helices will do that by themselves if you just program the sequences correctly. So let's zoom in on one of these connections here. And what you see is a junction, so-called holiday junction, and basically consists of 4 DNA molecules, or 4 DNA strands are involved in it. On the top, you have a blue DNA single strand. It has a certain sequence. It doesn't matter what it is actually. And then there's this purple strand, which reaches out and wraps around this blue strand here. And in order for that to happen, this blue molecule needs to have a complementary sequence that is partially complementary to this part of the blue molecule. And then basically, if that blue molecule happens to be then the second segment, which is partially complementary to this blue molecule here, then we'll form 2 double helical DNA domains. And you can do similarly with the orange molecule, and then you can build up such junctions. And this is sort of a very high-level description. In the real world, it's a bit more complicated than that, but in effect, using these kind of fairly simple principles, you can actually encode arbitrary structures in sets of DNA sequences. You know, it can be sets including 100 DNA single strands or 1,000 DNA single strands. The whole point is that the sequences of these DNA single strands are designed in such a way that as a system, they cannot build up the target structure by forming double helical DNA domains and placing junctions at user-defined positions. Then you can make these molecules, for example, by solid phase chemical synthesis or using biotechnological methods, and then you can put them into one pot, and then they will self-assemble in solution, and the structure will form. And this is an illustration of that process. It's not meant to be physically accurate. It's merely to show how that could unfold. So, and you kind of see here the two ingredients in a structure when it's designed according to a so-called DNA origami principle, which basically means that there will be a very long DNA single strand, which is depicted here in blue. It has a known sequence, and then you have many short DNA oligonucleotides called staple molecules, and they also have design sequences. And they are basically designed in such a way that they will fold this long DNA molecule into a shape which is fully encoded in sequences. So this approach, using long strand and lots of short DNA oligonucleotides, was originally invented by Paul Rotemund in 2006 in Caltech. And ever since, many people, including myself, have worked on this and advancing this method to different types of structures, as I will show you in a minute. Now, the structure that just formed here maybe not look very exciting. It's just a simple rod, 40 nanometer long, composed of 10 DNA double helices that are arranged in parallel. But the point of this is basically it's a fabrication method that allows you to plan with almost atomic accuracy a nanoscale structure in advance, and you will know exactly where each DNA base that's part of that, forming part of the structure, will be positioned in the context of that molecule. So it gives you a chemical specificity which you cannot really get with any other fabrication technique. And you can build a huge variety of structures using these or kind of adaptive principles. And what you see here is a portfolio of structures that we made over the last years in my laboratory. Everything that's blue or yellow consists 100% of designed DNA single strands. There is no point in basically being blue or yellow. It's merely just to look nice. But everything that's blue and yellow, that's all 100% made of DNA. Now, what you're seeing here flying around, these aren't models. What you see is actual data. So these structures have been solved experimentally using a method called cryo-electron microscopy single particle analysis. So I will explain that a little later. And so these structures actually exist and they look like that. And to give you a sense of scale, I've also included two objects here, the structures of two objects of natural origin. So they're called magenta. So on the top left, you have a little badminton ball type object that's actually a protein-based membrane pore. It has a molecular weight of 800 kilodaltons. And then more on the bottom right, there's this little magenta sphere. And that happens to be the hepatitis B virus core capsid. It has a diameter of 35 nanometer. And the point of that, showing that scale, is basically with DNA, modern day DNA nanofabrication, you can build objects that are really commensurate in size to that of natural macromolecular complexes. And that gives you interesting opportunities for applications, which I will talk about a little later. Now, as I mentioned, the origami was initially invented in the single layer, as a single layer concept. We call it sheet origami in 2006, so it's not exactly young anymore. So I was a PhD student at that time, and that paper inspired me so much that I went into that field and haven't left it ever since. I had the opportunity to contribute to a couple of advances in this field. So we learned how to build then multi-layer structures and curved structures and twisted structures, and how to design these and encode these kind of target shapes and sequences. However, at the time, the synthesis of these objects didn't work very well. So it was clear this kind of a proof of concept was made, but it's not useful for any application. So 3 years later, we learned how to actually fabricate these kind of objects also with high yields, with few defects, which was an important advance as it allowed to actually seriously contemplate some applications. Then we also added some methods that allow us to build, you can think of this as nanorobotic structures, or structures that you can build in such a way that they will have conformational degrees of freedom, and then that they can also be switched for different states. We learned then to push the performance of this whole design method to ever larger dimensions. So we learned to make assemblies which are actually even larger than viruses. And basically always trying to keep the defect rate low so that you can actually do something with that. We also learned how to make the raw materials required for the origami, and also the objects themselves, in a cost-efficient way, which is maybe a kind of mundane task, but it's very important, again, for looking into applications. So we have a biotechnological process that really allows you to grow the stuff in reactors using fermentation processes. We'll learn how to stabilize these structures so that you can take them out of the quite niche conditions under which they form into the real world, like, for example, in vivo conditions or other harsh environments. And lately, like last summer, we had another interesting advance. We actually learned how to fabricate actual motors and coat them in DNA nanostructures. So there was 2 papers published in summer where we made motors which can actually work on the environment. If depends on the timing, I may be able to talk about that. Anyway, so the progress in this field, not only from us, this is mostly our contributions to the field, but for many other groups in the world, is such that actually you can now start looking for industrial uses of these kind of objects. So in Munich, we actually have 3 spin-off companies which now pursue different directions based on DNA nanotechnologies. There is Tilibit. This is the first spin-off, was created in 2012. It's still alive. And it's doing business. It's not Google, but it's an honorable business. And then there's Capsutech and Photonic, which are both therapeutic projects. Then one thing I want to mention is like a key thing that helped us really over the years is something which I think should resonate here in the material science center is like everything you do, you need to precisely validate it. You're only as good in whatever you're doing if, as you're able to validate it. And so we have invested quite heavily into electron microscopy as a method to actually structurally analyze our designs that we're making so that we can make a feedback loop and refine our engineering principles so that we quickly get to build something that actually satisfies our specifications. So I want to briefly mention how that works. So we primarily use a method called cryo-electron microscopy. So what we do there was Nobel Prizes awarded for that, but maybe not everybody here in the room is familiar how that works. So I want to give you a high-level description. So basically, you have a solution, aqueous solution that contains the macromolecular complex, both structure you'd like to solve. So basically, you take a thin layer of that solution and you very rapidly freeze it. Basically, you have to do it so rapidly that the water doesn't crystallize, doesn't have time to crystallize. So then instead, it will form a amorphous phase called vitrified ice, which is like glass, but it's made of water molecules. And then embedded in that ice, basically, you have your target structure, ideally in random orientations. So then you can take that vitrified sample, you put it in a transmission electron microscope. It's very dose sensitive and everything, so there's a little bit of specialized equipment to do that, and then you just simply take images. And one of those images is shown here. You see this noisy background, that's the transmission contrast you get from water, and then you see there's obviously some particles embedded in it. And these are transmission projections of ideally the same type of object, suspended in different orientations in the ice. As if you were taking X-rays from your hand from different orientations, you get a transmission projection that will look different. So now you can use machine learning methods and algorithms to basically go automatically for huge data sets, pick individual particle photos, and try to combine them back into a common 3D structure. So then you get something like this as an intermediate step. You get sort of a 3D volume as it's being back projected from the individual particle data set, and then you also get a histogram that kind of will tell you how many particles in a data set have been assigned to particular views, transmission projections for your target object. Sometimes you also find that actually a data set contains multiple structures, cannot become made consistent with one structure, so all of these things are possible. So then if you have sampled all the different views, then you have a chance to actually get it doesn't advance. To actually, now advances to actually compute a structure, and then here's, for example, from the data set I just showed you, is just a barrel that we made for test purposes. And here the resolution is such that you can actually start to see the helical features of DNA double helices. You see major grooves and minor grooves and the connection between them. And you can, just another example of this kind of structure where we can see a decent amount of detail. So that's just a cube-weight that we made to understand how twist deformations develop in these kind of structures. And again, you get to a resolution where you can see really DNA double helices of all the beauty, like major grooves, minor grooves. You can see the connections. You can also see all all the flaws in that in this kind of structure. Like for example, the top. You can see there's some kind of defect here that truly wasn't designed, and you have this twist deformation. So if you don't like that, you can go back to design and refine your design. Here's a zoom in into that structure. So these are really the two key ingredients in DNA nanotechnology, which are DNA double helices and connections between them. So you may notice there's this little thing here in the center. So that's electron density, or density scattered by a single covalent bond. So this is a single covalent phosphide diester backbone bond from a DNA single strand, which holds the thing together. Now, if you have high quality data, you can start to build atomic models. So basically what we do, we have come up with a method we call that shrink wrap fitting. So we take our experimentally determined electron density map, which is shown here in gray. We filter it to low resolution. We construct a starting atomic model, and then we try to fit that using a cascaded relaxation process into an electron density. So basically move it in there, but then successively update the resolution of the constraint provided by electron density until we can really fit our atomic model into the experimental constraint. Now then, you basically have an annotated structure where you have a list of coordinates that sort of, and you can quantitatively evaluate the geometry. And that, for example, is the atomic model from the first version of that structure that we made. It has these twists, deformations, and some defects. So we went back to the design, we refined it and made version 2. And then version 2 is straight, and it doesn't have these defects. Now, this has no function, this particular object, but it's kind of demonstrates, I think, a key ingredient to engineering, the ability to actually go back, analyze the structure in detail, and make it meet your specifications. So, and that's possible with good material science instruments, like you find them in the center, I guess. All right, so now, having said that, I want to spend a few minutes on the subject of giant assemblies because it led to some applications. So we were just initially quite agnostically, application agnostic. We were, this doesn't really advance well. Let me just see where, yeah, now it goes better. I just dropped this. So in 2017, we invented a method how to make gigadalton scale gigantic cages out of DNA double helices. And just to make you appreciate the size, so this object we're seeing here, it contains 220 copies of a viral genome and about 50,000 DNA single strands. So it's a massive object, 1.8 million base pairs. And it still forms by self-assembly. And the whole thing is encoded in sequences. I think that was quite remarkable. This object, however, it didn't form very well, so the yields were low. It was merely like a proof of concept that we can make something that is as large as that. So we refined our approaches to make higher order assemblies, and we came up with something that we call programmable icosahedral shell canvas. Basically what we do is we build triangles out of DNA single strands, which you see in the top row. These triangles are shaped in such a way that they have beveled angles, and they have kind of shape complementary protrusions and recesses with which these triangles can interact with copies of themselves. And basically by playing with geometry, bevel angle, and edge interaction rules, you can make these triangles self-assemble into higher order shells. So everything on this slide is data. So all of these gray things here are cryo-EM structures that we solved experimentally, which kind of also implies that these structures form well, and they have a reproducible structure. So you can make octahedra, icosahedral shells, or larger icosahedral shells, which have like 60 copies of these triangles, for example. And this works really well. So if we look at the raw electron microscopy data, there's like a negative staining TEM micrograph. You see basically many of these icosahedral shells lying around, and they kind of look a little bit like viruses. I may view objects here which may be a little bit squished. This can be an artifact from the imaging, but it can also just be that some of these capsules were kind of a little bit defective. Now, if you have these shells, you can start thinking about doing something with them. So one thing you can do is, for example, is you can functionalize them with proteins. So this is one prototype that we made. We took this icosahedral shell platform and put 60 IgG antibodies on the surface of it with the FC fragments, or the crystallizable fragments of antibodies pointing away from the shell. Then you get something actually which looks like this. And again, it works so well that you can solve a cryo-EM structure of this icosahedral together with the proteins attached to it. So now this actually looks like a virus because it actually shares symmetry properties that you also find in natural spherical viruses. And it has proteins displayed in a certain copy number in geometry. So one thing you can think about doing with these kind of objects is you can try to think about building programmable vaccines. So you can think about positioning viral antigens like surface proteins from influenza viruses or other viruses on the surface of these kind of carrier structures, and then the expectation is that these kind of objects would lead to an immune response. The beauty of this is, however, that you don't need to actually, you don't need to learn how to deactivate a virus, for example, or you don't really need to understand a lot about target virus. You can just basically put it together and you do that vaccine. However, we didn't study that further because obviously there are now very good strategies to make vaccines, like based on the mRNA vaccine, so we put it basically on the back burner. Another thing you can do is you can make these structures such that you basically first build these icosahedra, and they're stabilized by DNA-DNA interactions. Then you add antibodies, and you can design a system such that the antibodies now actually stabilize these structures. So you make first the icosahedra, add antibodies, go to conditions where the DNA-DNA interactions break down, and then you have a structure which is kind of spring-loaded, but it's the antibodies that holds it in place. And the idea being that if you now add a soluble antigen to which these antibodies would respond to, they would be displaced from the shells, and you can set a cargo free if you had one. So this is what we tested. So we made a icosahedral shell. We included, for test purposes, actually hepatitis B core capsids. So actually we have a virus cargo contained in these shells, and they were stabilized by antibodies. Then we added a soluble antigen, which take oxygen in here as a test purpose, and these shells fall apart, setting free the cargo, which you can, which you can kind of see here. This was the cargo and all the components from the shells. Now, the vision of that is, imagine you can make a delivery vehicle which has some kind of drug payload, and you can add targeting moieties on the surface, and if you go into the vicinity of the target tissue or cell, then a displacement reaction could unfold, setting free the cargo, basically. It's like an antigen stim-triggered release mechanism. Now, what you can also do is you can stop the oligomerization of these shells so that instead of forming complete shells, they form partial shells. You can come up with a design solution that gives you half octahedra or half icosahedra or 3/4 of an icosahedron. And still, you can do it such that it works well enough that you can solve the cryon structure of that kind of complex. What can you do with that? Well, I can use that to actually trap viruses. So you can, for example, make a variant of these shells that are coated inside with antibodies, which are sticky for chikungunya virus particles, which maybe not many of you are familiar with. That's a virus disease which you typically find like in South America, for example. There's no treatment for it. And then basically you can mix these shells together with chikungunya virus particles and form a complex. And again, they work so well that you can solve a cryon structure of these two things together. So to me, this is very exciting because this really means we can do molecular engineering to make something that's even larger than a virus and make it even grab onto the virus. And then this is just some raw data to maybe make this more realistic, how that actually looks like. So all these spherical particles that you can see, hopefully you can see them, actually these are kind of chikungunya viruses, and then they're all nicely wrapped up into these shells. You can extend that principle and trap the whole zoo of shells of viruses. So, for example, we tested adeno-associated virus 2 as a cargo. So since these are rather small viruses, we put them into the half octahedra. We trap polioviruses, dengue viruses, noroviruses, human papilloma virus, SARS-CoV-2, chikungunya, which I already mentioned, rubella, adenovirus, and even influenza. Now, basically what you can see is depending on the size of the target virus, you simply pick the different shell prototype so that it would be slightly larger than the target virus. And one thing that's interesting here is for all of these viruses on the left-hand side, we use the same coating. It wasn't an antibody, we used a carbohydrate because it turns out that many viruses, not so publicly known, they have a background affinity to heparan sulfates, which is a particular type of polymers which you find on mammalian cells. Presumably there's some evolutionary pressure in place that sort of makes these viruses just be intrinsically sticky to these kind of polymers because that allows them to bump onto the cell and then maybe do a random search on the cell surface until they find the specific receptors. Like for example, SARS-CoV-2 seeks out these ACE2 protein targets, but sort of it also has affinity to these heparan sulfates. So the vision here is that you could conceive of a shell platform which is intrinsically sticky to viruses, but not to specific viruses, and could basically have some kind of broad spectrum antiviral activity. So speaking of which, the idea is that, of course, when you wrap up viruses, you can sterically inhibit interaction with cell surfaces. So we tested that idea, and we have the proof of concept data where we did in vitro neutralization with live viruses, with adenoviruses, hepatitis B viruses, influenza, chikungunya, the adeno-associated viruses, and lately also SARS-CoV-2. I want to show one example of how that data looks like. So in this graph, this is the result of a neutralization experiment done by virologists in high safety level environment using live chikungunya viruses. So this, what you see is a so-called dose response curve. On the y-axis, we measure the extent to which an antiviral compound was able to inhibit viruses from proliferating in cell culture. So there's ways to measure that. I'm not going to go into detail. And typically the virologists, then they plot this neutralization capability as a potency as a function of the concentration of the compound. So there's 3 data curves in this slide. So the blue data, that's empty shells. They have no specific functionality to actually stick to the viruses, so that they don't do anything. You can put them in as high concentration as you like. They won't cause any effect. Then in this proof of concept experiment, we used antibodies, which were raised against chikungunya viruses, not to have any neutralization capability, but it turns out they actually have some kind of neutralization capability. So if you use these antibodies here alone, they will eventually, at sufficiently high concentrations, inhibit the viruses from infecting cells, because they stick to the surface, and they do this kind of mechanical inhibition. Now, if you take these antibodies and you put them into the shells, you amplify the potency of neutralization drastically by orders of magnitudes. So this is basically coming from 2 effects. The shell material also contributes to occlusion, so it prevents viruses, and then also it creates avidity effects, which amplifies the interaction between the antibodies and the virus. So the vision is really, maybe we have an opportunity here to come up with something, I call it a plug-and-play antiviral. Take any virus binder, it can be a polymer, peptide, antibody, protein, host receptor domain, anything. Does need to have a little bit of affinity to target virus, but it doesn't need to be a neutralizing compound by itself. You can put it into these kind of shells, and then in principle, you should have a functional antiviral. That approach should be possible to neutralize any given virus. It should be quite resilient against virus mutations because of these avidity effects. And also, I think, an attractive aspect is you don't really need any detailed knowledge about the target or the target biology. You don't need to study the viruses a lot to actually do that. So we were so excited of this concept, so we thought we actually have to take this any further beyond writing papers, simply because if you don't, I would always feel bad for the rest of my life. So we make a company, and we're trying to make an actually real therapeutic out of this. So we're doing in vivo efficacy experiments at the moment, and we'll use this platform primarily to see where we can make these programmable antivirals. But there are other opportunities, like, for example, programmable delivery of drugs, as I pointed out, and also these kind of programmable vaccines, which we may look into later. So how's my time? 5 minutes? Okay, then I can show you one more thing, which is about the nanomotors. So actually, I studied physics, and I did photonics and stuff like that first, and I knew nothing about biology. Then by chance, I saw a talk by a famous Japanese professor called Katsuhiko Kinoshita, and this is one of the first biophysicists who actually showed that the ATP synthase, which I will explain what it is, actually is a rotary motor. So the ATP synthase is one of the most important molecular machines in nature. Every cell on Earth runs on ATP as energy currency. So every cell on Earth has ATP synthases, which are the enzymes that actually make ATP. And they do this in a quite remarkable fashion. So ATP synthases are localized in membranes, and they are driven by ion fluxes. So as you eat and breathe, there's a concentration gradient created across the membrane in the mitochondria, and this ion flux that ensues there drives rotary motion in these ATP synthases, and this rotation causes deformations in the molecular structures, which then allows them to bind to ADP and phosphate in such a way that you can catalyze a higher energy molecule, the formation of higher energy molecule. So I find this mind-boggling, and it's kind of, maybe one day we can do something from scratch. So the question is, can we build synthetic macromolecular motors that achieve similar functionalities? How can we power them? So then this is one thing I already mentioned, like in summer last year, we had were wrapped up like a 6-year-long research project, and it got published in Nature, which is nice and satisfying. It's not always possible that these exciting things get published in this way, but it's a Dinorigami rotary ratchet motor, which is a motor. And I want to briefly show you how it works. So the motor design is actually not that complicated. So it's basically a, it has this kind of pedestal here, and then it has a triangular platform, which has obstacles, and then you have this lever arm, which you can mount to this rotor dock, and basically it can rotate on top of the triangular platform, but the obstacles are in the way. And that's a key element to the operation of this motor. Then this is how it looks like with the actual real full-length lever arm in electron microscopy. So this triangular thing on the left, and then we have very long lever arm, and we mount fluorophores on the end of these lever arms so that we can actually watch the motion, the rotary motion, inspired by these famous experiments from Kinoshita, actually, in a fluorescence microscope. Now, let me show you some movies. So on the left-hand side, you can see basically a field of view where you have one rotary particle, and then there's this little dot that's the point spread function caused by the photons emitted from the fluorophores at the tip of these rotary arms. So then what we'll do is initially we'll have passive random Brownian motion of this motor, and then we turn on an energy input in the form of an alternating current. We just stick 2 electrodes of an alternating current in the solution. And then something interesting happens. So we track the motion. So this one does a random rotary motion, doesn't make any progress. But as we turn on the energy input, it's hard to see here, this one actually starts moving progressively in a counterclockwise fashion. I know that you can't see it, but it's true, so I have a slowed down version of that movie. Maybe now you can see it better. We can run it again. So now you can start to follow that. I think there's also a frame rate problem of how the data is transferred to the movie, but on my screen you can actually see it, but it really goes stepwise in a counterclockwise fashion. So this is going, it does progressive counterclockwise motion, and there's no information we supply to make it go this way. It does that because of the intrinsic properties of this design. Here's another example of this. I can kind of see that it's kind of futile to show it here because of this sort of frame rate problem, but this is an example which we made go clockwise. Once you turn on the electric field. Okay, so the slow motion, I'll skip that because I'm running out of time. So just to explain the phenomenology, so this motor works in a quite peculiar way. So basically, you have the motor body, it has a certain geometry and an intrinsic energy landscape, and you put it on the surface. Now, depending on how you orient the electrodes relative to the motor, you can make it go clockwise, you can make it stall, it won't have any progressive motion, or it can go counterclockwise. And this is kind of the data showing a whole ensemble of single particles that we analyzed this way that sort of shows this behavior. And now, one important thing is, of course, I mean, if such a rotary object does sustained rotation in a viscous medium, it's already delivering work, but it's not useful work because it's dissipated in friction. The question is sort of, for us was, can we extract some actual real work from these kind of motors? So we came up with an experiment, which is like basically winding a spindle. Like, you know, imagine you wind up your clock, mechanical clock. We made these motors we forced these motors to wind the Molker spindle. So the way we did this is we included a single strand of DNA, and then as we rotate this lever arm, it will just basically create tension in the single strand. And then this is the last slide I'm going to show. So you can do that, and then you turn on the energy input, it will wind the spindle, and as you turn off the field, it stalls and it goes in reverse. So that's really cool, because, I mean, it's quite noisy, but it's spectacular, right? You actually store the energy in a Molker structure, and then it can go in reverse. And that, yeah, that works. Yeah, that was nice. I think I speed up, so I'm going to go to the rest. How can I go to this? You showed me how that will work. Okay, now I got it. I want to show at least one thing, which is this slide. So I want to thank my team. So because these are all the amazing students and researchers behind the scenes who do all of this work. So I'm very thankful for all their contributions. Thankful to the funders, obviously, and you for your patience. Thank you.
Thank you for this brilliant, interesting talk. Anyone got any questions? Okay, there you go.
So thank you for that absolutely fascinating talk and great graphics as well. Question from me is, once you have the virus entrapped in that shell, what's the degradation mechanism for the complex? How does the body actually deal with that new entity?
Yeah, so that's a good question. So what happens basically also, like if you get infected with viruses, they're constantly being cleared using phagocytosis. So there's always these immune cells which eat up foreign particles, basically. So the mechanism will be the same. Basically, viruses which will be prevented from entering a cell, they will be cleared together with the shells and degraded in these phagocytes. So that's the approach. And there are engineering opportunities, like for example, monoclonal neutralizing antibodies, which are also being contemplated as therapeutics. They kind of enhance phagocytosis using because they essentially mark particles they stick to for uptake by the phagocytes. So that mechanism could also be exploited with these shells.
Any more questions?
Really exciting talk, thank you. I'm also interested in the DNA cages engulfing the virus and the mechanical properties of those DNA cages. I wondered if you could tell us a little bit about how they might respond to the mechanics in their environment and how that might be exploited for an application like catching these viruses and doing something with them.
That's a good question. So there's I can provide some circumstantial evidence to address that question. So we noted that basically depending on the target virus we were trying to engulf, we either deformed the virus or the shells. So obviously they have some kind of finite elasticity. So I think I'm not going to say any specific examples because I just may say wrong things, but you take a certain virus and somehow you flatten the virus to the shell walls, or the shells themselves get significantly deformed. So with influenza, for example, we have faced the technical problem that these are quite pleomorphic. They actually sometimes look like peanuts or like spheres and stuff like that. And basically there you need a malleable shell that can kind of accommodate that. And we made the prototype, which is on purpose was designed to be a little bit more floppy. So we kind of look into that, but we didn't really study that using FM dipping or things like that. We just pragmatically mix them with viruses and see what happens.
There's a lot more questions, but I think for the time's sake of this event, we can continue discussion with him personally over lunch in the poster sessions. So the next speaker is Damien. Yes. And he's going to talk about nanobubbles for therapeutic purpose. And
Cool. Thank you for the introduction. I'm Damien. You may have seen me around in the Bragg building a bit. I'm a postdoc working in the molecular and nanoscale physics group. I also did my PhD in the same group, so the work I'm going to talk about today is sort of overarching between my PhD and the past few months of this postdoc I've been doing. So the work that I've been doing essentially is looking at how we can use nanobubbles for the treatment of disease and infection combined with ultrasounds. So, as many of you might be familiar, there's a few sort of issues with disease treatment. So the main one we were focusing on in my PhD was for cancer. One of the main issues, or the sort of limiting factors of how effective cancer treatment is how much drug you can deliver to that tumour site. And there's a few things that sort of limit how much drug you can actually get in. First of all, sort of from a patient care sort of view, you've got systemic drug delivery, which leads to off-site toxicity. So you can't just pump someone full with loads of drug, because it will just make them really sick and lead to the side effects that we're sort of familiar with cancer. The other issue is that essentially cancer tumours have quite poorly formed vasculature, so it's hard to get drug in there, and they also have very high pressures in the centre of this sort of 3D tumour environment, which then tries to force drug out. We've also been looking at more recently at how we can treat bacterial infections, which have a sort of similar challenge presented to us as with cancer. we've been looking at biofilms, which essentially is any sort of growth of bacteria into this 3D structure on a solid fluid interface, and they have this really sticky extracellular matrix, which again makes it really hard to get drugs or any therapeutics in. So as I mentioned, we're wanting to want to use ultrasound combined with these bubbles for the treatment. Hopefully everyone here is familiar to some extent with the use of diagnostic ultrasound. So ultrasound is pretty low cost, widely available, provides real-time imaging, and it's non-ionizing, so therefore it's safe. And currently it can be used to aid disease diagnosis combined with ultrasound contrast agents, which I'll talk about on the next slide. Ultrasound can also be used for therapy. So there's a technique called HIFU, which stands for high intensity focused ultrasound. And essentially what you do here is you just focus very high energy ultrasound to a region, say on a tumor site, and then you can thermally ablate the tumor. However, there's current challenges associated with that just due to if you have anything in the presence of that beam path, you're not necessarily going to hit where you think you're hitting on the tumor. So these ultrasound contrast agents, or microbubbles at least to start with, these are basically micron-sized gas bubbles. They have a low solubility gas core, which helps to reduce the rate of gas diffusion from out of the bubble into the surrounding medium. They have a phospholipid shell, so these are basically little fat molecules that have a hydrophilic head and then a hydrophobic tail, and they self-assemble around at this gas-liquid interface, and they basically aid stability of the bubble and provide this physical barrier to diffusion of gas out into the surrounding liquid. We can also tune the acoustic or sort of ultrasound response of these bubbles by changing the lipid composition that we use to stabilize the bubbles. The other advantage of using these phospholipids is that we can add additional functionalization. So first of all, we can add a PEG chain, so just a polymer chain, to the head group of these lipids, which can help increase circulation time in vivo. And then again, using these PEG chains, and we can attach targeting molecules, so antibodies or apomers, which we can then specifically target certain types of cancer or infection. So a little bit of background just on sort of the basics of how ultrasound works. So ultrasound is high frequency sound waves. For ultrasound imaging in the most simplest terms, so beam mode imaging, basically it works on this pulse echo principle. So you send in a pulse of ultrasound, and at this interface between two materials that have a differing acoustic impedance, some of your wave gets reflected back, and this is how you construct the image. The more of this that gets reflected back basically increases the contrast of the image. So if you're looking between different types of soft tissue, the reflection is very poor, and this leads to poor contrast. However, if you look at the impedance mismatch between soft tissue and gas, which obviously is very low density, you get almost 100% reflection of the wave. So I've got an example here just showing how this works for our ultrasound contrast agents, which obviously have a gas core. So we have this thing here called a tissue mimicking phantom, basically just something that has similar acoustic properties to tissue, and we have this tube running through the middle. And you can see, if this plays, hopefully, that as we flow bubbles through the tube, you can see them scattering the ultrasound back, and we can then use this to track blood flow in vivo. But what's interesting about these bubbles is they're essentially, they have a gas core, so they're compressible to some degree, and our ultrasound is basically this oscillating pressure field. And what this means is these bubbles undergo volumetric oscillations, and they behave as a driven oscillator. Quite fortunately, the resonant frequency of these bubbles lies within the clinically approved range for ultrasound, so typically between 1 to 10 or 15 megahertz, which is really good for their sort of scattering properties. These bubbles also have quite interesting acoustic response, so you can look at basically how they oscillate in response to that ultrasound, and they emit ultrasound frequencies at the fundamental frequency we've driven them at, but they also do it at harmonics, so some sort of integer values of that driving frequency. And what this means is that with our imaging techniques for our ultrasound, we can use harmonic imaging techniques to basically remove any of that linear response you would get from tissue and just be left with the harmonic response that you get from bubbles to improve contrast and basically just see where the bubbles are. The sort of for our aim where we want to use them for therapy, the fact that these bubbles oscillate is quite interesting, because if you have an oscillating bubble, it will induce localized fluid flow, and if you've got a membrane nearby, so for example a cell membrane, you exert shear forces on that cell. And we can utilize this to essentially enhance the uptake of drugs into cells. So we've got an example here of some 3D cancer models, and we've delivered doxorubicin, which is a chemotherapy drug shown in green here. And you can see that the combination of doxorubicin with our bubbles and our ultrasound leads to increased accumulation of doxorubicin in our cancer cells, and then leads to increased rate of dead cells and enhanced uptake. However, delivering drugs like this systemically does lead to toxic side effects, but what we can do is we can load our drugs into these liposomes, so these are small lipid nanoparticles which have an aqueous core. We can then attach them to the bubble and then use these to use the ultrasound to trigger release of the liposomes from the bubble and then deliver the drug to the tumour site as well, which then helps to increase the effectiveness of the treatment but also reduce that off-site toxicity. However, the main focus of the work that I've been doing has been on nanobubbles. So these are basically any bubbles less than 1 micron in size. You can separate these from a mixed population of bubbles, basically based off the fact that bubbles float, and how fast they float to the top of a vial or whatever is proportional to their size. So your big bubbles float to the top really quick, and you get left with your small bubbles at the bottom. From their sort of theranostic or therapeutic potential, these smaller bubbles are quite interesting because it means they can perhaps reach places that our larger microbubbles couldn't reach before. So microbubbles are typically restricted to the vasculature, and that means they can't penetrate deep into the tumour. However, these nanobubbles have the potential to pass through gaps in the endothelial lining and start to accumulate in the tumour, which then we can trigger release of the drug and hopefully improve the effectiveness of our treatment. From a more fundamental point of view, as I am meant to be a physicist, basically, you have the Laplace pressure, which I think was mentioned in the talk earlier. This is basically the pressure difference between the inside and the outside of a bubble. As you decrease the size of your bubble, this Laplace pressure increases. So, for example, if you have a 2 micron diameter bubble, this pressure difference is around 0.2 atmospheres. However, if you take your bubble down to 100 nanometers, this rapidly increases to 4 atmospheres, and this essentially drives instability of the bubble. So we have the question to ask, are these bubbles stable? Why are they stable? And also, how do we know that they are bubbles and they're not some sort of liquid droplet instead? So what size are nanobubbles? I said before they're less than 1 micron in size, which I guess isn't typically nano. However, if you look across the literature, basically the size of these bubbles varies massively. So some studies, they're looking at 100 nanometer bubbles, and some of them are up to 800 nanometers in size. There's also some issues where people claim to have nanobubbles and then show you images like this, where you have bubbles. If you look at the scale bars here, they're 10, 20, 30, 40 microns in size, very much not nano. And this is a problem if you want to compare between studies, because the sheer stress an oscillating bubble exerts is non-linearly proportional to its size, as is the resonant frequency of their bubble. So you can't compare their therapeutic or their diagnostic performance across these studies very well. The reason their size varies so much, first of all, the way that people isolate these bubbles from mixed populations varies quite a lot, but also it's quite hard to characterize these bubbles accurately. That's what I'll talk about over the next few slides. So the way that we make these bubbles is we start off with this solution of liposomes. So these, again, they're lipid particles with an aqueous core. We then use some sort of technique to turn these into bubbles. So mechanical agitation or microfluidics are the two main techniques we use in our labs. And then you end up with this population of big bubbles, small bubbles, and some liposomes that didn't get turned into bubbles. You then use some isolation technique to remove those larger bubbles, and you get left with your nanobubbles and then some leftover liposomes in there as well. So normally for microbubbles, people use optical microscopy to characterize them. So an image here just of bright field images of some bubbles in solution. However, when you're using nanobubbles, they're typically smaller than the sort of resolution that you have of a bright field microscopy system, and you don't really see anything. However, what we can do is we can utilize light scattering techniques to observe the Brownian motion of the particles. So perhaps the most common light scattering technique, at least for sort of these types of studies, is dynamic light scattering, where you basically look at the Brownian motion of a sample in bulk just by shining a laser through it and looking at a photodetector and see how that light intensity varies. However, because it's a bulk measurement technique, we can't distinguish between bubbles, non-bubbles. It's just looking at whatever is in that solution sort of in general. There is another technique that we have as well called nanoparticle tracking analysis, which follows a similar principle, except here you use an objective to basically image the scattered light from individual particles and then track their Brownian motion. So you can get sort of a distribution looking like this, looking at the size and concentration of the particles and count how many there are. However, you still can't distinguish nominally between what is a liposome, what is a bubble. And you can see here we have the comparison between the liposome precursor solution versus what we turn into nanobubbles. Initially using NTA, you can't really see any difference between the two. However, you have to then consider what's different about these bubbles and how we can use that to try and characterize them or at least distinguish them from non-bubbles. So first of all, obviously the bubbles have a gas core, and this means they have a different refractive index to water or to a liposome. So what we did basically is we thought, well, because of this, the scattered light from a bubble should be approximately 40 times greater from that of a liposome if they're the same size. We then utilised the NTA system and used it in a slightly different way to sort of conventional methods, and we basically dropped the camera gain down really low and bumped up the concentration of our sample during the measurement. And we showed that if you looked at the liposome sample with no bubbles in, you can't see anything at these settings. But then at the same settings, you can see, after you turn them into bubbles, you can see these highly scattering particles, which suggests we've made something, at least, that scatters a lot more light than our liposomes. So this here is an example distribution from the NTA system of our nanobubble sample, so around 200 nanometers in size. We then also wanted to show that these particles are acoustically active, so that they're gas-filled or at least respond to ultrasound. So we basically use high-intensity focused ultrasound to just destroy the bubbles, basically just blast them with loads of energy to rupture and destroy the bubbles. And you see before and after doing this, the concentration of our sample drops by an order of magnitude or 2. So it suggests we have something in there that scatters a lot more light than liposomes and also is acoustically responsive. There's also another technique called resonant mass measurement, and this basically looks at the physical properties of the bubbles. So they have, obviously, your gas bubble has a different density to your liposomes. This technique basically works off having a resonant cantilever with a small microfluidic channel flowing through, and as particles flow over this, you then change the mass of the cantilever, which then changes the resonant frequency. And then depending whether or not the density of your particles is greater or less than your medium, you get a frequency shift in one direction or the other. Based off the magnitude of this frequency shift as well, you can then determine the size of the particles. What we see is by putting our samples in here, you can very nicely sort of split it into these two subpopulations of what we call positively buoyant particles, so those that will float. Hopefully these, or they should be bubbles, and then also negatively buoyant particles, so liposomes or droplets, or anything else you have in there. But we can see fairly confidently that we do have these positively buoyant particles in our sample. Unfortunately for us and for the field, this system has been discontinued, which is a shame, but we do have one in our labs. So if anyone wants to use it or get involved, open for collaborations. So moving on to what we've actually done with these bubbles rather than just characterizing them, most recently we've looked at how does nanobubble size affect drug uptake, if there is this problem in the field of the size sort of varying wildly. So for this we used microfluidics, so it's essentially a small channel. We grew some cancer cells on the top and then we flowed through some nanobubbles, and then we used this fluorescent sort of, I guess, membrane probe or molecule, which is just dextran, to see if we could get this into the cells with our bubbles. So you see that, so on the green we've got some live cells. After ultrasound treatment only with the dextran, there's very minimal uptake of dextran into the cells. However, the combination of our nanobubbles and our ultrasound, you can start to see the sort of co-localization between the dextran fluorescent signal and that of the live cells. We then looked at how the size of the bubbles affected that amount of drug uptake into the cells, and we saw it works across a range of bubble concentrations, but the trend you get isn't what you would necessarily expect. So you would think bigger bubbles will behave better than smaller bubbles, but we saw this weird intermediate phase for the sample in green, where the smallest bubbles started to outperform the others at certain concentrations. I won't go into too much detail now, but we basically started to investigate some weird things we started to see with the stability of these bubbles and how this maybe disagrees with classical bubble sort of stability theory. We also use these bubbles to trigger drug release from liposomes. So we created these particles called nested nanobubbles, where we encapsulated a bubble within a drug-loaded liposome, and then through the application of ultrasound, the idea is this bubble oscillates, ruptures the liposome, and you get drug release. So we got drug release over a range of pressures compared to our control sample of just liposomes without a bubble inside. And what we saw, quite interestingly, was that if you look at the change in release between the sort of the bubble sample and the control sample, the max value we get to for the encapsulation, the max value, sorry, for the release is equivalent to the encapsulation efficiency of the bubbles within the liposomes. So not every liposome has a bubble in, but it was around 20% of them did, and that's the max value we got for this change in release. So you can sort of hand-wavingly say that we get 100% release efficiency from every liposome that has a bubble in. So what we're doing at the moment, which is the main focus of the postdoc I'm on in this EPSRC grant, we're basically looking at how we can use these bubbles to treat Staph aureus biofilms or infections. So biofilm is this sticky sort of infection stuck on a surface, quite hard to treat. Biofilms typically found on the surface of implanted medical devices are also found in the heart, so infections like endocarditis, and they're quite hard to treat. Currently, what happens is someone gets diagnosed with sepsis, you take a sample of their blood to culture, in the meantime you give them a mix of antibiotics until you get those culture results back, and then you give them directed antibiotics. But what we propose is that we can use our bubbles with these specific targeting molecules on to, first of all, stick to the infection site, and do specific binding to the type of infection that it is. We can then use our ultrasound imaging to locate that infection site and find where it is, and then we can then use higher intensity ultrasound to then start to physically eradicate that biofilm from the surface, and then combine this with other sort of therapeutic treatments for the biofilm. So some quick conclusions. Trying to distinguish between gas-cooled bubbles and aqueous-cooled liposomes is quite hard, but we've shown that we can use a commercial NTA instrument to do this. We've also used resonant mass measurement to identify positively buoyant particles in a bubble sample as well, and we can use these bubbles to enhance drug delivery into cancer cells, as well as trigger drug release from liposomes. And the future work is using these bubbles to locate an infection site and deliver a therapeutic payload. So thanks to my PhD supervisors, all the people on the Beatstron project that I'm on now, so collaborators who helped with some of the work that I've just shown, and also thanks to all of the MMP group for the past 5 years of research, I guess. And yeah, if anyone's interested in any collaborations for any of these techniques or any interesting ideas, please speak to me after or just send me an email. Thank you.
Well done. Thank you for the bubbly talk. Yes. Okay, time for 2 questions. Or just one.
Nice talk. A couple of suggestions, actually, one of which, your top point about distinguishing between the bubbles and the liposomes. You might be able to add something to the continuous phase, to the water, to refractive index match your liposome, and then you'll only see the bubble.
Yeah, I had a recent one for the last time I did a similar talk saying exactly the same thing.
The other one, the other one being, you talked about the bubble size. The other thing is the size distribution, because they'll undergo Oswald ripening, so that will change. So as well as thinking of the size, think of the distribution on that, because that will change your properties quite dramatically.
Yeah, I think it's an issue as well with classical theory, and you really look at single bubble behavior, not a big group player. You will get that Oswald ripening, which we see to an extent.
Thanks.
I guess we'll have to move on to the next sessions for lightning sessions. Okay, so more discussion with Damien over lunch, yes.
Okay, so I think we need to conduct our lightning session at lightning speed. Can I ask all of our lightning presenters to gather at the front here, please? Okay, we ready? As ready as we'll ever be. Okay, so our first speaker is Yenglang Yu.
Hi, I'm Zhen Liang, PhD student from School of Civil Engineering, University of Leeds. As you know, the alkaline activated material is low carbon cement for reducing the CO2 emission. Therefore, the characterization of its pore network is not trivial in terms of understanding its reaction mechanism and predict its life service. However, conventionally, the characterization of the porosity is determined by applying the destructive technique, which is not realistic. Therefore, it can be overcome by using the micro-CT techniques. By using the machine learning method, we can successfully segment the 3 phases and calculate the volume fraction of each phases, and then have its pore network to have the pore size distribution of the connected pores and the isolated pores. The connected pores will then be used in the modeling work to predict its life service, like stimulate its carbonation and the chloride ingress. Besides, the synchronous XRD-CT technique can provide the 3D maps. Each means each technique can contain unique diffraction patterns, resulting in localized information on crystalline phases. In these cases, we would like to focus on one crystalline phase called the entrite, which is a key secondary reaction product in porcelain cement and sodium sulfate activities like cement. By constructing 3D maps of entrite distribution, we could physically and chemically say how this crystalline phase changed under the carbonation process. Therefore, this technique, XRD-CT, can bridge the gap between the characterization of physical and the chemical aspect in a non-destructive way. If you have interest in my research, please check the poster number 34. Thank you very much for your attention.
Thank you very much. Next up is Samuel.
Recent developments in solid-state nanopores have favored numerous strategies that enable single-molecule detection of a wide range of analytes. However, they often lack the ability to provide quantitative information of heterogeneous mixtures, where nanostructures of different sizes are present, which often is the case in analysis of folded supramolecular DNA nanostructures. In my research, we explored this challenge by taking advantage of DNA origami folding technique to create high-order DNA assemblies, like in a little Tetris game at the nanoscale, where we make use of a fixed nanopore not only to detect and discriminate DNA nanostructures with different assembly degree, but also to provide quantitative information about the assembly yield of each nanostructure present in a respective mixture. And we do this in a rapid, high throughput, and label-free manner. To find out more how we do this and our approach to implement this with nanopores, and the meaning behind the scoreboard of Tetris, come to visit my poster. Thank you.
Thank you. Next up is Joseph.
Hi everyone, I'm Joe. I'm in the molecular nanoscale physics group and I work with Professor Evans. We're looking at developing in vitro adaptive therapy model for colorectal cancer. So if we consider conventional chemotherapy in this blue bar on the top, if treatment Dietz is given to a tumour that's made of two types of cells, the red sensitive cells and the black resistant cells, we see that when treatment's given at repeat doses, we're removing the sensitive cells and giving these black resistant cells a reduced competition. So they're kind of thriving and the tumour's becoming resistant. Adaptive therapy, so there's been a lot of modelling done to show that if we were to give a time delay between the treatments to let those sensitive cells recover, they will give a bit of a hindrance and give some resistant competition to the black cells to try and prolong the time before a tumour becomes resistant. But this, of course, you need some kind of feedback mechanism to say, well, how long should that time be? So what we're looking to do is to make a lateral flow assay which would detect a biomarker given out by colorectal cancer cells. So the idea is we generate our disease model, we'll measure the marker of interest with our lateral flow assay, and then we'll ask the question, is the marker above the threshold level? And if not, we'll give no treatment and go back down to the measurement stage. But if the marker is above a threshold level, we'll administer our treatment, so we'll take the orange path. So some of the work I've been doing, the first part of my PhD was split into looking at detection. So we've found new ways to synthesize quite novel gold nanoparticles. So we've got gold nanosheets, gold nanopine cones, and gold nanotips. And we've applied these to a lateral flow assay for a biomarker for colorectal cancer. And the next kind of thing that I've been looking at is similar to Damien, looking at microbubbles for colorectal cancer treatment. So when we inject microbubbles with drugs and apply ultrasound, we can punch small pores in the cells, which boost the uptake of these drugs, and then we can image. So I've got some live dead stain of colorectal cancer cells there, and the next step is just bringing it together. So can I use this lateral flow to inform when's the best time to apply the bubble treatment? Yeah. Thank you very much.
Thank you very much. Next up, we have Aisha.
Hi everyone, I'm Aisha. I'm a PhD student and I work on self-assembled cartesian and DNA origami nanostructures against antimicrobial resistant bacteria. So what I have done is that the continuous emergence of the bacterial resistance has pushed us to find novel therapeutic strategies. One of them is the gene therapy antisense approach, but the delivery of the antisense to the bacteria is very crucial. So what we are doing is we have prepared a polyelectrolyte complex composed of two different biopolymers. One is the DNA origami, and the other one is a cationic chitosan to form a polyplex structure to act as a vector and deliver the antisense in bacteria. So I've used a 6 helical bundle to complex with chitosan using two different chitosans, and we have formed a hybrid structure for that, and the conformation of the complex is achieved through zeta potential results. And then we have also characterized that structure using asymmetric flow field fractionation, which was coupled with different detectors. We use multiple angle light scattering to determine the gyration radius and the online DLS to determine the hydrodynamic radius of the structure, and both these radii were used to determine the conformation of the complex structures, and then we confirmed those structures through TEM imaging, which shows fibrillar structures of the hybrid. And the next, what we're going to do is we're going to functionalize these structures with antisense and deliver them in bacteria. Thank you.
Thank you very much. Next up is Atripsa.
Hello everyone, my name is Atisa Pabuntan. Have you ever heard of a material that can change its property? Just a simple change in the temperature. So let me introduce you to the vanadium dioxide. When a pure vanadium dioxide is in its low temperature, the insulating monoclinic phase is allowed the visible light and the infrared spectrum to pass through. But however, when the temperature reaches 68 degrees, it undergoes structure phase transition into a metallic rutile phase. In this phase, the material reflectivity increases. Imagine having a mirror that becomes more reflective as it gets hotter. In addition, when a tungsten ion are introduced into the crystal structure of vanadium dioxide, the phase transition temperature is lowered, making it more sensitive to the temperature change. So this enhancement can lead into the development of the new kind of application. Smart window made with the thermochromic vanadium dioxide can help reduce energy consumption in the building by controlling the light and the heat passing through them, or the optical switches that can turn on and off in the moment of the notice, or even the infrared sensor that can be made more sensitive with the temperature change. So I hope you find vanadium dioxide interesting materials as I do. Thank you.
Thank you. Next up we have Madhan.
Hi everyone. My name is Muhannad. I'm part of the CDT CP3, and today I'm going to speak a part of my PhD project. So as we know that around 84% of the world's energy need is currently met from fossil fuel combustion. That's why green hydrogen gas fuel is urgently needed to displace the fossil fuel-based economy. And one of the ways to meet the global demand is to use industrial waste such as H2S and photosplit it into hydrogen gas and elemental sulfur. And in our methodology, we have developed cadmium sulfide and terbium-doped cadmium sulfide quantum dots, which were dispersed in a borosilicate glass matrix. And these were used as a photocatalyst for the splitting of H2S into H2 gas and elemental sulfur. This is a schematic of our experimental setup. This experiment was performed in Pune, India, where H2S is bubbled through a photoreactor containing 0.5 molar KOH solution, and quantum dot glass particles were dispersed in this photoreactor. So upon excitation, holes are produced in the valence band and electrons are being produced in the conductance band, and these undergo redox reactions with the HS anion to form the hydrogen gas. Here is just a quick summary of our hydrogen evolution results when we used 0.5 gram of the catalyst. Well, what we can see here is that when we change the composition of the quantum dots in the glass matrix by the addition of the terbium ions, the hydrogen evolution rate changes. And when we heat treat these quantum dots in the glass matrix, they grow in size, and this causes an increase in the size of the quantum dots, which decreases the hydrogen evolution rate. We have also studied the photostability of these by running one of the samples for 4 different cycles. And as you can see that in the 4 attempts, no significant changes occurred to the hydrogen evolution rate, which indicates that doping such quantum dot materials in a borosilicate glass matrix preserved its photocatalytic properties. Thank you.
Thank you very much. Thank you very much. Next up is Philippe.
Hi, I'm Philip. My project research focuses on the corrosion investigation of spinal instrumentation. What is spinal instrumentation? On the top left, you can see it. It's an implant system consisting of various screws and rods. It's used to treat low back pain, spinal instability, and also deformity. There are various complications associated with this kind of implants, for example, loosening, fracture, or corrosion. Damage in general can occur where modular metallic components are in direct contact. When we take a closer look into this interface, we can see that micromotion leads to particle release and ions, which then result in adverse body reactions. So the aim of my project is to investigate and understand these implant degradation processes and also the implant particles associated with it. In my experiments, I simulate micromotion in a screw rod interface in kind of a threading drivometer cell. The particles, the parts are exposed to different electrolytes, simulating inflammatory conditions in the body. When we see the 3D scans of the samples after the tests, we can see that the inflammatory conditions are quite more severe and we have more material loss. From the threading results, we can see that the friction results are similar. The electrochemistry shows us that the inflammatory conditions are quite more severe and we have more corrosive degradation at the interface. In total, we can see that the interface suffers more of corrosive degradation, and in future we also will have a look into particles originating from them. Thanks.
Thank you. Next up we have Joe.
Hello everyone, my name is Chao Sun, a second year PhD student from the School of Chemical and Process Engineering. My talk about millifluidic synthesis of proton conduction softnet metal organic frameworks. So in my PhD study, I'm really interested in developing material solutions to reduce carbon emissions. Fuel cells as renewable energy conversion devices have attracted people's attention due to their long cycle life and good safety nature. Membranes can determine the power density and operation conditions of the fuel cell. And naphthalene is currently the most commonly used membrane, but it has disadvantages of hazardous manufacture and high production costs. So I'm looking at metal organic frameworks or MOFs as an alternative to naphthalene to overcome its limitations. So you can see the top picture. MOFs are comprised of metal or metal clusters and organic linkers. So they are primarily developed as a porous materials, but they also offered a way to create solids with controlled chemical properties by incorporating functional groups, such as a softnet group, a sulfur and 3 oxygens bonded with carbon. This group can provide proton hopping seeds to promote proton transfer in the material. And the continuous synthesis presents a way to achieve scale-up synthesis of MOFs because this method allows for faster and safer reactions. Based on this knowledge, I continue to synthesize a copper-based softnet MOF by using the silicon oil as a second phase to avoid any falling or clogging problems. The continuous synthesis can be operated more than 5 hours with consistent yield and particle size. And also, our collected sample presented promising proton conduction. So if you would like to find out more of my continuous synthesis, please check my poster. Thanks.
Thank you very much. Next up is Johan.
Thank you. I'm Johan. We'll do a quick look at some current EV lubricant research. So, EVs contain a lot of copper, and there's an issue in that current lubricants contain a lot of sulfur. We need to remove this sulfur, but this changes the tribofilm quite significantly because sulfur is used to bond the tribofilm to the surface. The tribofilm being a protective, wear-resistant layer that's formed in situ on tribological contacts, such as in gear teeth. You can see testing the low sulfur lubricants. In A, we see a drop at 10 millimeters per second, which is indicative of tribofilm damage. We're able to reduce this damage by increasing the polarity with the use of esters. B, but a further increase in polarity to C, we see the damage returning. This is also slightly time sensitive in that the yellow results are taken at later time periods, so we see that even where we get damage, these tribofilms do stabilize over time. Thank you.
Thank you. Next up we have Diana.
Hello everyone. Physiological engineering approach for synthetic bone scaffold. Basically the work is focused on the repair and reconstruction of critical size bond defects larger than 5 centimeters, where there is high risk of delayed bond healing, compromised healing, or non-union at all. However, extensive research has been done in this area, but unfortunately, none of the designed material or scaffolds could accurately mimic the biological and mechanical properties of natural bond. Therefore, in this work, and based on the diamond concept of bond healing, we are trying to develop a new composite material following the powder metallurgy with the space holder technology by mixing titanium powder with bioactive mineral, in particular the iron-doped brushite. The porosity characterization done by SEM and microcity showed the optimal porous structure, which should support vascularization and cell penetration at the defect site. The mechanical properties were comparable with that of natural cortical bone, and the numerical work was promising, in particular when we got the uniform stress distribution across the scaffold compared to the natural bone. Also, we can see with the strain results how scaffold deformed and supported load transfer to the bone, and that would be significantly helpful to support bone growth. In vitro experiments, we can see how osteoblast cells were growing on the scaffold surface, and that in particular by increasing the porosity and mineral ratio. At the moment, we are working on animal trial, we are working on rapid femur bone, and hopefully by spring 2023, the results will be ready. Thank you so much.
Thank you very much. Next up is Palinda.
Hello everyone, my name is Pavinda. I'm from School of Dentistry, and I work with human enamel, and these are made up of enamel rods that are made up of these hydroxyapatite crystals, and over time with acid attack, this crystal starts to erode and hence causes enamel erosion, which is the disease that I'm looking at. And in my project, I am trying to test the abilities of these three ionic species to see how they can, what role they play in enamel remineralization. And I'm part computational and experimental. So in computational lab, I'm using CASTEP to model this enamel and do substitution in it and see how good these models and and test their capabilities in remineralizing. And from these models, I saw that when strontium is substituted in these models, it gave me a negative formation energy indicating that it is stable and it will give me positive results in laboratory, whereas with other ions, it was the formation energy was positive, indicating that they are unfavorable. So I translated these results in laboratory using these techniques, and I tested the role of strontium with human enamel, and I saw that the crystals that are formed with these experimentations are a bit more broader and a bit more wider in width, and also the presence of strontium was shown by the EDX spectra, which is shown here. And if you have any more questions, please come to my poster. Thank you for listening.
Thank you very much. Up next is Ben.
Hi, my name is Ben Q. I'm from the School of Food Science and Nutrition. So there's a greater need to increase our plant proteins in our diet for a number of reasons: sustainability, animal welfare, and also health. However, if many of you may know, plant proteins can be quite distasteful. They have off mouthfeel, astringency, and this has been related to friction values. So a field called tribology, which is the field of lubrication science. So what we can do is we can take these plant proteins and we can put them through a microgelation procedure. So what this is we hydrate proteins, so protein isolates, we heat them, so they form a gel, and we can then homogenize these to nanometer-sized particles. So what does this do, and what effect does this have on their performance? So when we compare these to native structures, their lubrication decreases by an order of magnitude, which is amazing. And we also compared this to a 20% oil in water emulsion, so similarly to single cream. And the lubrication was not significant, if not better than this 20% oil in water emulsion. So this microgelation procedure not only improves plant proteins compared to native plant proteins, but it also creates new applications in terms of potential fat replacement and new possibilities for plant proteins in food.
Thank you very much. And last but not least is Sebastian.
Yeah, fantastic. Last one, it's me here. Last two talks are speaking about food and stuff just before lunch. That's fantastic. So basically, yes, so we are looking into the application of tribology, as Ben mentioned about it, in terms of, in this case, for chocolates and stuff. And then tribology in general has got, it can improve health condition, also has got application in informing, making foods better and more tasty. We recently looked into the tribology of chocolates, and which received a reasonably well attention from media. And it was featured in like around more than 300 news outlets, BBC, CNN, and Daily Mail as well, which proved that we are doing something legit. Anyway, so we looked into the two, basically we broke down the procedure into the three main stages, which was leaking, by the way, that's me, and molten plus saliva when it's mixed with the biological fluid. And we looked into it across two scales, which was a single papillae, which is a roughness around tongue, and also with the tongue mimic material, which we developed in our group. And then we came to a conclusion based on our observation across the stages and scales that we can basically produce chocolates. It's more important that where we put the fat content rather than the amount of the total fat content. And we propose a design to hopefully produce more healthy chocolates with hopefully minimum compromise on the taste. And lastly, one just video, which doesn't show that, unfortunately, on a in situ kind of a live trigonometry microscopy, which we developed with Mike over there from mechanical engineering, showing basically why dark chocolates are perceived as gritty. The reason being, before the video starts, I think Andy will promise us some chocolates probably in lunch. Do we have chocolates in lunch? Yeah, so basically it shows that we would have these solid particles in the chocolates, which can be trapped between our tongue, papillae, and the roughness of our tongue. That's important.
I think he's telling us it's time for lunch.
And yeah, so that gritty nature is coming from the solid particles in the chocolate. Thank you.
Thank you. Thanks, Okay, well, I agree with the presentation. It's definitely time for lunch. I think we should all thank our lightning speakers again one more time for catching us up on a bit of time. And now it's time to head to the refectory. The events team downstairs will help usher us across. Thank you.